Hello there, and welcome to Science for Sleep, where curiosity slows down just enough for your mind to wander comfortably, and science takes its time so you don't have to. Tonight, we're exploring something that sounds simple at first, almost like a question you might hear in a classroom or during a quiet late-night conversation, but the deeper you go, the stranger it becomes. We're going to gently ask, and then patiently follow, a single idea. What is the fastest thing in the universe? It sounds like the kind of question with a quick answer, doesn't it? You might already be thinking of something. Perhaps light, maybe a spaceship, or even something more imaginative. And yet, as with many things in science, the moment you try to hold the answer still, it starts to shift slightly, like trying to catch a reflection on water. Before we go any further, I'd like to ask you something simple, just to ground us in this moment. Where are you listening from right now? And what time is it in your part of the world? Maybe it's late evening, maybe very early morning, or somewhere in between where the day hasn't quite decided what it wants to be yet. It's a little fitting, really, that we're talking about speed, while all of us are sitting still in different places, moving through space faster than we usually realise, without feeling it at all. If you find this kind of slow exploration calming, or if it gives your thoughts something gentle to follow as you wind down, I'd really appreciate it if you left a like or subscribed. It helps this quiet corner reach more people who might need a softer place to land at the end of their day. Now, there's something slightly amusing about asking what the fastest thing in the universe is, because in our everyday lives, speed feels very straightforward. A car moves faster than a bicycle. A plane moves faster than a car. A falling object seems faster than something drifting slowly in the air. We compare, we measure, we decide. Fast or slow, simple. But the universe, as it turns out, doesn't always follow our simple categories. Let's begin somewhere familiar. Imagine you're standing on the side of a quiet road. You hear a car approaching in the distance. At first, it's just a faint sound, barely noticeable, and then gradually it becomes louder, clearer, more present. A moment later, the car passes you, and then the sound fades away again. Now imagine the same scene, but this time you don't hear anything at all. You only see the car. It appears in the distance, moves toward you, passes and disappears. The experience is different. The timing feels different. Even though the car hasn't changed its speed, your perception of it has. Already, without realizing it, you're dealing with two different kinds of fast. The speed of the object itself, and the speed at which information about that object reaches you. That difference is going to matter more than you might expect. Because when we ask what the fastest thing in the universe is, we're not just asking about objects moving from one place to another, we're also asking about how quickly anything can travel, including light, energy, and even information itself. And that's where things start to get interesting. Think for a moment about how you experience the world right now. Everything you see, every object, every colour, every movement, is actually reaching you through light. Light leaves an object, travels across space, and enters your eyes. It feels immediate, but it isn't truly instant. There's always a tiny delay, even if it's so small that you'll never notice it. When you look at something across the room, the light takes a fraction of a second to reach you. When you look at the moon, that light has been travelling for just over a second. When you look at the sun, you're seeing it as it was about 8 minutes ago. So even now, without trying, you're already looking slightly into the past, which is a strange thought, but also a gentle one, and it raises a question that sits quietly beneath everything else we're about to explore. If there is a limit to how fast things can travel, what does that mean for everything we see, everything we know, and everything we experience? To get there, we need to take a small step back and think about speed itself, not in terms of numbers or equations, but in terms of how we understand it. Speed, at its simplest, is just distance over time, how far something travels divided by how long it takes to get there. It's a very human way of measuring motion. We use it every day without thinking. Kilometers per hour, miles per hour, seconds, minutes, hours. But the universe doesn't really care about our units. From the perspective of the universe, Motion is not about roads or destinations, it's about relationships. One thing moving relative to another, one frame of reference compared to a different one. For example, you might feel like you're sitting completely still right now. Maybe you're lying down or resting comfortably, not moving at all. But at the same time, the Earth beneath you is rotating. It's spinning at hundreds of meters per second, depending on where you are. On top of that, the Earth is orbiting the Sun at about 30 kilometers per second, and the Sun itself is moving through the galaxy at an even greater speed. So even though you feel still, you're actually moving incredibly fast through space. It just doesn't feel like it. And that's one of the first clues that speed is not always what it seems. Our brains are very good at simplifying things. They take complex motion and turn it into something manageable. Stillness, movement, fast, slow. But those labels are always relative. They depend on where you are and what you're comparing things to. A plane feels fast when you're standing on the ground watching it pass overhead, but inside the plane, it feels calm, almost motionless, as if you're sitting in a quiet room that just happens to be moving. So when we start asking about the fastest thing in the universe, we have to be careful. Fast compared to what? From whose perspective? Measured how? Because once we leave everyday experiences behind, those questions become more important than the answers themselves. Now, if you were to gather a group of people and ask them what the fastest thing in the universe is, most would probably say the same thing: light. And that's not a bad guess. In fact, it's very close to the truth. But like many things in science, the deeper you look, the more that simple answer starts to unfold into something more layered. Light doesn't just happen to be very fast. It has a special role in the structure of the universe itself. It sets a kind of boundary, a limit that nothing else seems able to cross. But we're not quite ready to step into that just yet. Before we get there, it's worth spending a little more time with the idea of speed as we experience it, because it helps anchor everything that comes later. Imagine again that you're watching something move, maybe a train passing by. At first, it's distant, moving slowly across your field of view. As it gets closer, it appears to speed up, even though its actual speed hasn't changed. Then, as it moves past you, it seems to rush by quickly, before slowing down again as it disappears into the distance. This is a simple effect of perspective, but it shows how easily our perception can be fooled. What feels fast isn't always what is fast, and what feels slow isn't always slow. Now extend that idea further. What if something were moving so fast that your brain couldn't quite keep up with it? What if it crossed a distance so quickly that it almost seemed to vanish and reappear somewhere else? At that point, speed stops feeling like motion and starts feeling like something else entirely, something closer to a limit, and that's where the story begins to shift. Because there is, as far as we know, a maximum speed in the universe, a speed that nothing with mass can reach or exceed, a speed that defines how information travels, how cause and effect unfold, and how the universe itself is structured. And yet even that statement comes with a few quiet complications, because while nothing can move through space faster than this limit, space itself might not follow the same rules, and there are situations where things appear to move faster, even if they're not truly doing so. So the simple question, what is the fastest thing in the universe, slowly becomes a more subtle one. What does fastest actually mean when the universe has rules that don't quite match our intuition? We'll take our time with that. For now, it's enough to notice that speed is not just about motion. It's about perception, measurement, and the limits of how things can interact. And as we move forward, we'll start to narrow in on that limit, not in a rushed or technical way, but step by step building a clearer picture of what fast really means on the largest scale possible. Because somewhere between the quiet motion of everyday life and the extreme conditions of the cosmos, there is a boundary. Not something you can see or touch, but something that quietly shapes everything around you. And once you begin to notice it, even the simplest things like light crossing a room or a signal reaching your phone start to feel a little more meaningful. It's a curious thing, really, how confidently we use the word fast in everyday life, as if it were something obvious, something solid, something that doesn't need much thought at all. A car is fast, a train is faster, a plane faster still, and beyond that, perhaps a rocket, disappearing into the sky with a kind of quiet finality, leaving behind a trail, and the feeling that it has crossed into a different category altogether. But if we pause for just a moment and look a little closer, the idea of fast starts to loosen its edges. Because what does it actually mean for something to be fast? At first glance, the answer seems straightforward. Something is fast if it covers a large distance in a short amount of time. That's the simple definition. Distance divided by time. A neat little equation that has served us well for centuries. It's how we measure cars, runners, aircraft, and even the wind. And yet, even in that simple definition, there are assumptions quietly sitting underneath. Distance, measured from where to where. Time, measured by whose clock. It's easy to forget that both of these depend on perspective. Imagine for a moment that you're sitting comfortably on a train. The ride is smooth. There's no noticeable vibration, no sudden movement. Perhaps you're looking out the window, watching the landscape pass by slowly. Or maybe you're not looking at all, just resting, eyes closed, feeling still. From your point of view, you're not moving. And in a very real sense, that's true. But to someone standing outside watching the train rush past, you are moving very quickly. Dozens, maybe hundreds of kilometers per hour. From their perspective, you're part of something fast. So which one of you is correct? The answer is, quietly, both. Speed is not something an object simply has on its own. It's something that only exists when you compare one thing to another. Motion is always relative. Fast compared to something else. Slow compared to something else. There is no universal sense of at rest. And this is where the idea begins to shift from something intuitive to something a little more subtle. Because if all motion is relative, then even something that seems completely still, like the ground beneath your feet, is actually moving in ways that are far beyond what you can feel. Right now, wherever you are, the Earth is rotating. If you're near the equator, you're moving at about 1,600 kilometers per hour just by standing still. And at the same time, the Earth is orbiting the Sun at about 30 kilometers per second. 30 kilometers every single second. It's the kind of speed that would feel unimaginable if you could experience it directly. And yet, you don't feel it at all. There's no wind rushing past you, no sense of acceleration, no indication that you're moving at all. Your body, your surroundings, everything moves together, and so your brain simplifies the experience into something manageable. Stillness. And this is one of the first quiet clues that fast is not something absolute. It depends entirely on what you're measuring against. Now, let's take that idea and stretch it just a little further. Imagine two people standing on opposite sides of the Earth. Each one feels still. Each one sees the world around them as stable and unmoving. But from a broader perspective, both are moving through space at incredible speeds, carried along by the rotation and orbit of the planet. Neither of them feels fast. Neither of them feels slow. Because without something to compare themselves to, speed becomes invisible. And this is where things begin to connect with our original question. When we ask what the fastest thing in the universe is, we're not just asking about objects moving quickly. We're asking about the limits of comparison itself. The point at which speed stops being relative and starts becoming something more fundamental. But before we get there, it's worth noticing how our perception of speed shapes the way we think about it. Because in everyday life, speed is not just about numbers. It's about feeling. Think about the last time you were in a car on a highway. When you first start moving, even a moderate speed can feel fast. The surroundings blur slightly. The sensation of acceleration is noticeable, and your attention sharpens. But after a while, something changes. Your brain adjusts. What once felt fast begins to feel normal, comfortable even. And if the car slows down, it can suddenly feel like everything has become sluggish. Even though the speed might still be quite high, this adaptation happens constantly, often without you realizing it. The same thing happens when you're on an airplane. At cruising speed, you're traveling at around 800 or 900 kilometers per hour. That's far faster than anything most of us experience on the ground, and yet, inside the cabin, it feels calm, quiet, almost motionless. You might be sipping a drink, reading, or even sleeping, completely unaware of the incredible speed at which you're moving through the sky. So again, what does fast really mean? If something can feel slow while moving at enormous speed, then speed alone isn't the whole story. There's also context, there's also perception, and there's something else that becomes important as we move beyond everyday experiences, the way information travels. Because when you see something moving, you're not actually observing the object directly. You're observing the light that has travelled from that object to your eyes. And that light takes time to get there. For most things in daily life, that delay is so small that it doesn't matter. It's effectively instant. But as distances grow larger, that delay becomes more noticeable. When you look at a distant mountain, you're seeing it as it was a fraction of a second ago. When you look at the moon, you're seeing it as it was just over a second ago. And when you look at distant stars, you're seeing light that has been travelling for years, sometimes even millions or billions of years. So the very act of seeing is tied to speed, the speed at which light travels, and suddenly the idea of fast begins to take on a different role. It's not just about how quickly something moves from one place to another, it's about how quickly information about that movement can reach you. And that distinction matters more than it might seem. Because in physics, there's a fundamental difference between something moving through space and information travelling across space. And while many things can move very quickly, there appears to be a limit to how fast information itself can travel, a limit that nothing seems to surpass. This is where the idea of a fastest thing starts to become meaningful in a deeper sense. Not just the fastest object, but the fastest possible way for anything to happen, to be known, to influence something else. Because speed, at its core, is about change. One thing affecting another. A cause leading to an effect. A signal travelling from one place to another. And if there is a maximum speed for that process, then it becomes something more than just a measurement. It becomes a rule, a boundary, a quiet constraint built into the structure of the universe itself. But we're not quite there yet. For now, it's enough to notice that fast is not as simple as it first appears. It's not just a number on a speedometer. It's not just a feeling of motion or a blur of passing scenery. It's something that depends on perspective, on context, and on the way information moves through space. And once you begin to see it that way, even ordinary moments start to feel slightly different. A passing car, a drifting cloud, the glow of a distant light. All of them are part of a larger system of motion and interaction, shaped by limits that are not immediately visible, but always present. So as we move forward, we'll keep that in mind. Because the question we started with, what is the fastest thing in the universe, isn't just about finding a single answer. It's about understanding what fast really means when you step outside of everyday experience and begin to look at the universe on its own terms. There's something quietly unreliable about the way we experience motion, something that most of us never really question, simply because it feels so natural. You move, things move, the world shifts around you, and your brain does a remarkably good job of turning all of that into a smooth, understandable experience. So good, in fact, that it rarely feels like interpretation at all. It just feels like reality. But if you slow things down, just a little, and start paying attention to how motion actually feels, you begin to notice that it's not nearly as consistent as it seems. Let's start with something simple. Picture yourself sitting in a parked car. The engine is off. Everything is still. You can see the road ahead, maybe a few buildings, maybe trees swaying gently in the distance. Nothing is moving around you, and your body feels settled, grounded. Now imagine that another car pulls up beside you, and for a moment it begins to move forward very slowly. there's a brief instant, almost like a flicker in your perception, where you might feel as if you're the one moving backward. It's subtle, and it usually passes quickly, but it happens often enough that most people have experienced it at least once. And it raises a quiet question. If your brain can momentarily mistake someone else's motion for your own, then how certain can you be about what's actually moving at any given moment? This isn't a flaw exactly, it's more like a shortcut. Your brain is constantly trying to interpret motion based on relative changes. It looks at what's shifting in your field of view, compares it to your expectations, and builds a best guess of what's happening. Most of the time, that guess is correct. But sometimes, especially when there are few clear reference points, it can be just slightly off, and that's where things start to get interesting. Because motion, as you experience it, is not just about what's physically happening, it's about how your brain constructs a story from limited information. Take another example. Imagine you're on a train again, sitting by the window. Another train passes on the adjacent track. For a moment, the two trains are moving at similar speeds, and the outside world seems to drift by slowly, almost lazily. Then, as the other train speeds up or slows down, your sense of motion shifts. The world suddenly appears to accelerate or decelerate, even though your own train hasn't changed speed at all. Your experience of motion is being shaped not by absolute movement, but by comparison. And this happens constantly, often without you noticing. When you're walking down a quiet street, your movement feels steady and clear. But if you step onto a moving walkway at an airport, something changes. Your body adjusts, your sense of pace shifts, and for a moment your brain recalibrates what normal movement feels like. The same thing happens when you're in an elevator. At the start, when it begins to move upward, you feel a slight heaviness, a gentle pressure pushing you downward. When it stops, there's a brief sensation of lightness, as if gravity itself has loosened its grip for just a second. But once the elevator is moving at a constant speed, those sensations disappear. You feel still again, even though you're moving vertically through space. So what you actually feel is not speed itself, but changes in speed. Acceleration. Your body is sensitive to motion when it starts, when it stops, or when it changes direction. But steady motion, even at high speed, fades into the background. And this is one of the most important pieces of the puzzle, because it means that fast is not something your body is naturally equipped to detect in a direct way. What you feel is change. What you notice is difference. But constant motion, no matter how fast, can become invisible to your senses. This becomes even clearer when we look at something like air travel. At cruising altitude, an airplane is moving incredibly fast, hundreds of kilometers per hour, and yet inside the cabin, everything feels calm. There's no rushing wind, no sense of speed, no indication that you're moving at all. You could close your eyes, and aside from the gentle hum of the engines, you might imagine yourself sitting in a quiet room. The speed is there, undeniably, but your experience of it has been smoothed out, filtered, simplified, and this leads to an interesting realization. If your senses can't directly detect constant speed, then your understanding of motion is always going to be incomplete. You rely on external cues, visual references, and changes in movement to build a picture of what's happening. Without those cues, speed becomes something abstract. Now let's take this a step further. Imagine you're floating in deep space, far from any stars, planets, or visible landmarks. There's nothing around you, just darkness. You're inside a spacecraft, moving at a constant speed. How fast are you going? From your perspective, there's no way to tell. You feel no motion. You see no passing objects. There's no wind, no resistance, no sound. As long as your speed remains constant, your experience is identical to being completely at rest. This is not just a thought experiment. It's a fundamental principle of physics. There is no experiment you can perform inside a closed system that will tell you your constant velocity. Motion, once again, is relative. And this has a subtle but important consequence. It means that the idea of fast doesn't really exist in isolation. It only exists when something else provides a reference point. A road beneath your feet, air rushing past your skin, stars drifting across your field of view. Without those references, speed disappears from your experience entirely. Now, there's another layer to this, one that's a little more unexpected. Your perception of motion is not only relative, it's also delayed. Every signal your brain receives takes time to arrive. Light enters your eyes, travels through the optic nerve, and is processed by your brain. Sound waves reach your ears, are converted into electrical signals, and interpreted. This all happens very quickly, but not instantly. So, in a very real sense, you're always experiencing the world slightly after it happens. The delay is tiny, far too small to notice in everyday life, but it's there, and your brain compensates for it. It predicts, it anticipates, it fills in gaps to create a continuous experience of motion, even though the information it receives is always just a fraction behind reality. This predictive ability is incredibly useful. It allows you to catch a ball, avoid obstacles, and move through the world smoothly. But it also means that what you perceive as motion is not a direct recording of reality. It's a carefully constructed interpretation, a best guess, and like any guess, it can be influenced by context, expectation, and prior experience. For example, if you watch a fast-moving object, like a ball thrown across a room, your brain doesn't just passively observe it. It actively predicts where the ball will be next, allowing you to react quickly. In some cases, your brain even slightly shifts your perception of where the object is, aligning it more closely with where it expects the object to be. So what you see is not just what is happening, but what your brain believes is about to happen, which is a remarkable thing when you think about it. It means that motion, as you experience it, is not just physical, it's cognitive. It's shaped by processes that are constantly working behind the scenes, smoothing out inconsistencies, filling in gaps, and keeping your experience coherent. Now, all of this might seem like an interesting detail about human perception, but it connects directly to our larger question. Because if our experience of motion is relative, delayed, and constructed, then our intuition about speed is not always reliable. We can be easily misled by what feels fast or slow. Something that appears to move quickly across our field of view might actually be moving slowly at a great distance, and something that feels slow might be moving at an extraordinary speed, just without obvious reference points. So when we begin to explore the fastest things in the universe, we have to be careful not to rely too heavily on how motion feels. Because the universe doesn't operate according to our perception. It follows its own rules, and those rules are not always aligned with our instincts. It's interesting how, without really thinking about it, most of us already carry around a quiet sense of what fast looks like. Not in numbers, not in equations, but in experience. A car accelerating onto a highway feels fast. A train passing by at full speed feels faster. An airplane lifting off, climbing into the sky, carries a kind of weight to it, a sense that it belongs to a different category entirely. And then there are moments like standing near a rushing wind or watching something fall quickly, where speed becomes less about movement and more about sensation. All of these experiences build a kind of internal scale, a reference system. And it's this everyday scale that shapes how we imagine speed long before we ever think about the universe. So let's spend a little time with it, because understanding these familiar limits helps make everything that comes next feel more grounded. Imagine you're driving along a quiet road. At 30 kilometers per hour, everything feels calm. The scenery passes slowly. You can notice details, houses, signs, small movements on the sidewalk. There's time to think, to react, to observe. Increase that to 60, then 80, then 100 kilometers per hour, and something shifts. The world begins to compress. Objects pass more quickly. Your attention narrows. You become more focused on the road ahead, less aware of the smaller details around you. the sense of speed isn't just about motion anymore. It's about how much information your brain can comfortably process. Go faster still, and your field of attention tightens even more. You stop noticing things at the edges entirely. The experience becomes centered, forward-facing, streamlined. This is one of the first quiet limits we encounter. Not a physical limit, but a cognitive one. Your brain can only process so much information at once. As speed increases, your ability to take in and respond to your surroundings becomes more constrained. Reaction times matter more. Small delays become significant. So in everyday life, speed is not just about how fast something can go, but how fast we can safely handle. Now, let's take that idea and extend it to different forms of movement. A bicycle, for example, rarely exceeds 20 or 30 kilometers per hour under normal conditions. At that speed, you feel connected to your environment. The wind is noticeable. The ground beneath you feels present. You're part of the motion. A car, moving at highway speeds, separates you slightly from that experience. You're enclosed, protected, insulated. The speed increases, but your direct connection to it decreases. An airplane takes that separation even further. At cruising speed, you're moving at around 800 to 900 kilometers per hour. That's nearly 10 times faster than a car on a highway. And yet, inside the cabin, it feels almost still. You might be sitting comfortably, perhaps even asleep, completely unaware of the immense speed carrying you across continents. So already, something interesting is happening. As speed increases, your experience of it often becomes less intense, not more, which is the opposite of what you might expect. Now let's consider sound. Sound travels much faster than anything we usually interact with directly. At sea level, it moves at about 343 meters per second, which is roughly 1,235 kilometers per hour. That's faster than a commercial airplane. But we don't usually think of sound as fast in the same way. We hear it all the time. It feels immediate, almost instantaneous. When someone speaks, the words reach you without noticeable delay, at least over short distances. But if you've ever watched something happen at a distance, like fireworks or a thunderstorm, you've seen the separation. You see the flash first, and then, a moment later, you hear the sound. That delay is sound taking its time to reach you, and even though it's moving quickly by everyday standards, it's still slow enough for you to notice the difference. This gives us another layer to our understanding of speed. Something can be incredibly fast compared to human-scale movement, and yet still be slow compared to something else, and that comparison is where the idea of limits begins to take shape. Because in everyday life, there are practical limits to how fast things can move. Cars are limited by engines, friction, and safety. Airplanes are limited by aerodynamics and fuel efficiency. Even bullets, which move much faster than most things we encounter, are constrained by materials and physics. And then there's something called the speed of sound itself, which acts as a kind of barrier. When an object moves faster than sound, it creates a sonic boom, a sharp, sudden release of pressure waves. This happens because the object is moving faster than the sound waves it produces, essentially outrunning them. For a long time, this was considered a significant boundary. Breaking the sound barrier wasn't just about going faster, it required new designs, new understanding, and a willingness to push beyond what seemed like a natural limit. But once it was achieved, it became clear that this was not a fundamental limit of the universe. It was a limit of a medium. Sound travels through air. Its speed depends on the properties of that air, temperature, pressure, density. Change the medium, and the speed changes too. In water, sound travels faster. In solids, faster still. So the limit wasn't absolute, it was conditional, and that's an important distinction. Because as we move toward the idea of the fastest thing in the universe, we're not just looking for something that happens to be very fast. We're looking for something that represents a true boundary, a speed that doesn't depend on conditions, materials, or environments, a speed that remains the same no matter what. But before we get there, it's worth noticing how all of our everyday experiences fall within a relatively narrow range. From walking speed to highway speed, from airplanes to sound, everything we encounter operates within limits that are comfortable for human perception. Even the fastest things we build or observe directly are still, in a cosmic sense, quite slow. That might sound surprising at first. After all, a jet travelling at hundreds of kilometres per hour feels incredibly fast. A supersonic aircraft breaking the sound barrier feels even more extreme. But these speeds, impressive as they are just small steps on a much larger scale. To get a sense of that scale, imagine something moving 10 times faster than a jet, then 100 times faster, then 1,000 times faster. At each step, the numbers grow, but our intuition struggles to keep up. Because our everyday experience doesn't prepare us for those kinds of speeds. And this is where the transition begins. Everything we've talked about so far, cars, planes, sound, even the fastest human-made objects, exist within a range that is limited by materials, energy, and the environments we operate in. These are practical limits, but beyond them, there are deeper constraints. Rules that don't come from engineering or biology, but from the structure of the universe itself. And once we move into that territory, the idea of speed changes again. It stops being about how fast we can go and starts becoming about how fast anything can go. Because somewhere beyond the speed of cars, beyond the speed of sound, beyond even the fastest objects we've ever created, there is a boundary that doesn't shift, doesn't depend on conditions, and doesn't bend to our intuition, a limit that everything else seems to respect. There was a time, not so long ago in the grand sweep of human history, when the world felt a little smaller, a little quieter, and in many ways a little slower. Not because things were actually moving more slowly, but because our understanding of motion had not yet stretched far enough to notice what lay beyond it. In that world, long before airplanes crossed continents in hours, and long before signals travelled invisibly across the globe, sound held a kind of quiet authority. It was one of the fastest things people could directly experience, measure, and trust. If something happened at a distance, sound was often the first clear sign that it had occurred. Imagine standing in an open field during a storm. You see a flash of lightning tear across the sky, bright and sudden, and then, a few seconds later, the sound arrives. A deep rumble or a sharp crack rolling across the landscape. Even without knowing anything about physics, people understood something important from this. There was a delay, and that delay meant that sound travelled. It didn't appear instantly, it moved. And once you realise that something moves, the next natural question is, how fast? For much of history, answering that question wasn't easy. There were no precise instruments, no electronic sensors, no high-speed cameras. There were only observations, simple tools, and a great deal of patience. But even with those limitations, people began to notice patterns. They saw that sound arrived faster over short distances and took longer over larger ones. They noticed that echoes bounced back from distant surfaces, returning after a measurable pause. And they began to connect these observations into a rough understanding that sound had a speed, even if they didn't yet know exactly what that speed was. One of the earliest attempts to measure it came from something quite straightforward: distance and timing. If you could create a sound at one point, observe it from another, and measure the delay, you could begin to estimate how quickly it was travelling. This might involve something like watching a distant event, a hammer striking metal, a cannon firing, and then counting the time until the sound reached you. Simple, but effective. Over time, these kinds of experiments became more refined. By the 17th century, scientists in Europe were conducting more controlled measurements. They used synchronized observations across known distances, often involving gunfire or other sharp sounds, to determine how long it took for the sound to travel. And gradually a number began to emerge. Sound moves through air at roughly 343 meters per second. That might not sound especially fast compared to the speeds we're familiar with today, but in the context of human experience at the time, it was remarkable. Faster than any animal could run, faster than anything that could be thrown, built, or directly controlled. It was, in a very real sense, one of the fastest phenomena people could reliably observe, and because of that, it carried a certain weight. Sound became more than just something you heard. It became a way of understanding motion and distance. For example, sailors at sea could estimate how far away a storm was by counting the seconds between lightning and thunder. Soldiers could gauge the distance of artillery fire. Even in everyday life, the delay between seeing and hearing something became a quiet tool for interpreting the world. It gave people a sense of scale, a way to connect events across space, and for a time, it seemed like one of the fundamental limits of how quickly anything could travel. But there was something else happening at the same time, something less obvious but equally important. People were beginning to notice that sound behaved differently depending on its environment. In colder air, it moved more slowly. In warmer air, a little faster. In water, faster still. And through solid materials like metal or wood, it could travel even more quickly. This was a subtle but crucial realization, because it meant that the speed of sound was not fixed. It depended on the medium it was travelling through, and once you understand that, the idea of sound as a universal speed limit begins to weaken. It's no longer an absolute boundary, it's a property of a specific system, a feature of air or water or whatever material is carrying the vibrations. Still, for a long time, this didn't diminish its importance. Sound was fast enough to feel immediate, but slow enough to reveal its movement. It sat in that comfortable middle ground where human perception could grasp it. You could experience it directly. You could measure it. You could build an intuition around it, and that intuition shaped how people thought about speed in general. If sound had a speed, then perhaps other things did too. If sound took time to travel, then perhaps all signals required time. But there was something quietly puzzling about this, because there was another kind of signal that didn't seem to behave the same way. Light. At first, this difference wasn't obvious. For most everyday situations, light appears to arrive instantly. You see something, and it's simply there. No delay, no waiting, no counting seconds between cause and effect. This led many early thinkers to assume that light either travelled infinitely fast, or that its speed was so great that it might as well be instantaneous. Compared to sound, which revealed its movement through delays and echoes, light seemed almost magical, unbounded, unconstrained. And so, for a while, sound remained the most tangible example of something moving quickly through space. It was the fastest thing people could interact with in a direct, measurable way. But as observations became more precise, small inconsistencies began to appear. Astronomers, for example, started to notice slight delays in the timing of celestial events, particularly in the motion of Jupiter's moons. These delays couldn't be explained by errors in measurement or simple mechanical models. Something else was happening, something that suggested that light, like sound, might also take time to travel. And if that were true, then the entire picture would begin to change. Because if light had a speed, and if that speed was much greater than that of sound, then sound would no longer hold its place as the fastest known phenomenon. It would become something else, a stepping stone, a way of understanding how waves move through a medium, how information travels, and how limits can emerge from physical systems. And that shift from sound to light marks one of the most important transitions in our understanding of speed. But before we fully step into that, it's worth pausing here for just a moment, because there's something quietly elegant about the role sound played in this story. It gave us our first real sense that motion is not instantaneous. It introduced the idea that signals take time, and it showed us that speed can be measured, compared, and understood, even with simple tools and careful observation. In a way, sound taught us how to think about speed. It gave us the language, the intuition, and the curiosity needed to ask deeper questions. And without that foundation, the leap to understanding something as fast as light might have felt far more distant. Something began to feel slightly off the moment people started looking more carefully at the sky. Not in a dramatic way, not all at once, but in small, quiet inconsistencies that didn't quite fit with the idea that everything we see happens instantly. Up until that point, light had been treated very differently from sound. Sound clearly moved. You could measure it, hear the delay, track its travel. But light didn't seem to behave that way at all. You open your eyes, and the world is simply there. A candle across the room, the moon in the sky, the distant horizon. All of it appears immediately, without any sense of travel or delay. There's no waiting, no counting seconds, no gap between cause and effect. So for a long time, it felt natural to assume that light didn't really have a speed in the same way sound did. Or if it did, it must be so incredibly fast that it might as well be instant. That idea held on for quite a while. Even some of the greatest thinkers, including people like Isaac Newton, leaned toward the belief that light travelled either infinitely fast or so quickly that its motion couldn't be detected with the tools available at the time, and honestly, it made sense. Because if you tried to measure light over everyday distances, across a room, across a field, even across a city, the delay would be so small that it would be impossible to notice. It would always appear instantaneous. So the question lingered quietly in the background. Does light actually take time to travel? Or is it fundamentally different from sound? The answer, as it turned out, came not from something close by, but from something incredibly far away. It came from the motion of a distant planet and its moons. In the late 17th century, a Danish astronomer named Ole Remmer was studying the movements of Jupiter's moons. One of these moons, Io, orbits Jupiter in a regular, predictable pattern, almost like a clock. By observing when Io passed into Jupiter's shadow and reappeared, astronomers could track its orbit with impressive precision. At least that was the expectation. But Remmer noticed something strange. The timing of these events wasn't perfectly consistent. Sometimes Io would appear a little earlier than expected, sometimes a little later. At first glance, it might have seemed like an error in measurement, or perhaps a flaw in the understanding of the moon's orbit. But the pattern wasn't random. It followed a rhythm. When Earth was moving closer to Jupiter in its orbit, the events seemed to happen earlier. When Earth was moving away, they appeared delayed. And slowly, a realization began to take shape. The difference wasn't in Io. It wasn't in Jupiter. It was in the light itself. When Earth was closer, the light had a shorter distance to travel. When Earth was farther away, the light had to cross a greater distance, and that extra distance meant extra time. It was a subtle effect, spread across enormous distances, but it was enough to reveal something profound. Light does not arrive instantly. It travels, and it travels at a finite speed. This was a turning point, not just because it answered a question, but because it introduced a completely new way of thinking about the universe. If light takes time to reach us, then everything we see is slightly delayed. Every observation is, in a sense, a glimpse into the past. The sun you see is not the sun as it is right now, but as it was about 8 minutes ago. The stars you see at night are not as they are in this moment, but as they were years, centuries, or even millions of years ago. And suddenly, the universe becomes layered in time. Distance is no longer just space, it's also history. But there was another question waiting just behind this discovery. If light has a speed, how fast is it? That question turned out to be much more difficult to answer. Remmer's observations gave the first estimate, but it wasn't very precise. It showed that light was incredibly fast, far faster than sound, but not infinite. Over time, other scientists refined the measurement. One of them, Hippolyte Fizeau, devised an experiment in the 19th century that attempted to measure the speed of light here on Earth. His method was clever. He used a rotating toothed wheel and a distant mirror. Light would pass through a gap in the wheel, travel to the mirror, reflect back, and pass through the wheel again. By adjusting the speed of the wheel, he could determine how long it took for the light to make the journey. It was a delicate setup, requiring careful alignment and precise timing, but it worked. For the first time, the speed of light was measured directly on Earth, and the result was astonishing. Light travels at approximately 300,000 kilometers per second. That's 300,000 kilometers every single second. To put that into perspective, light can travel around the entire Earth about 7.5 times in just 1 second. It's a speed so far beyond everyday experience that it almost stops feeling like motion altogether. And this is where everything begins to change. Because once you know that light has a speed, and that this speed is not just very large but consistent, always the same, no matter where you measure it, a new question emerges. Why? Why should light have this particular speed? Why not faster? Why not slower? And more importantly, is it just a property of light, or is it something deeper? As scientists continued to explore this, they discovered something unexpected. The speed of light doesn't depend on how fast the source is moving. If you shine a flashlight while standing still, the light travels at this constant speed. If you shine it while moving forward, the light still travels at the same speed. Even if you could somehow chase the beam of light at incredible speeds, the light would still move away from you at exactly the same rate. This is not how most things behave. If you throw a ball while running, the ball's speed adds to your own. It moves faster relative to the ground than if you had thrown it while standing still. But light doesn't follow that rule. Its speed remains constant, and this constancy is what makes it so special. It's not just that light is very fast, it's that its speed appears to be a fundamental feature of the universe itself, a kind of built-in limit, a boundary that nothing else seems to cross. And once this idea takes hold, it leads directly to one of the most important developments in physics. Because if the speed of a light is always the same, regardless of how you move, then our usual understanding of space and time can't be quite right. Something has to adjust. Something has to give. But that's a step we'll take a little later. For now, it's enough to sit with this realization. There was a time when sound felt like the fastest thing we knew, a reliable, measurable limit grounded in everyday experience. And then, gradually, quietly, that understanding expanded. Light entered the picture, not just as something faster, but as something fundamentally different. Something that didn't just move quickly, but defined what quickly could even mean. It might feel a little counterintuitive at first. Up to this point, speed has always seemed like something that can, at least in principle, keep increasing. A faster car replaces a slower one. A more powerful engine pushes the limit a bit further. Even when we run into barriers like friction or air resistance, we tend to think of them as challenges to overcome, not absolute boundaries. So when we arrive at the idea that light has a specific speed, and not just a very high one but a fixed, unchanging one, it naturally leads to a simple question. Why that speed? Why does light travel at about 300,000 kilometers per second and not faster? And perhaps more intriguingly, why doesn't anything else seem able to go beyond it? At first glance, you might expect the answer to involve something like resistance, as if space were subtly slowing things down, or some hidden force acting like a cosmic speed limiter. But that's not what's happening. In fact, light doesn't have a limit in the way we usually think about limits. It doesn't reach a maximum speed after accelerating. It doesn't gradually approach a boundary. Instead, it simply always moves at that speed. No build-up, no delay, no variation. From the moment light is created, it travels at this constant rate. And that's what makes the question a little unusual. We're not asking why light can't go faster, but why this speed is built into the universe in the first place. To get a sense of this, it helps to shift perspective slightly. Rather than thinking of light as something moving through space, imagine that its speed is something more like a property of space itself, a built-in feature. A bit like how the stiffness of a material determines how sound travels through it. Earlier, when we talked about sound, we saw that its speed depends on the medium. In air, it moves at one speed. In water, faster. In solids, faster still. That's because sound is a vibration, a ripple moving through something that already exists. Light is different. It doesn't need a medium in the same way. It can travel through empty space, where there is nothing to carry it. So instead of being limited by a material, its speed seems to be defined by the structure of space itself. And this is where things begin to feel a little less like everyday experience and a little more like the underlying rules of reality. In the 19th century, scientists studying electricity and magnetism began to uncover patterns that hinted at something deeper. One of the key figures in this work was James Clerk Maxwell. Maxwell developed a set of equations that described how electric and magnetic fields interact. These equations revealed that changes in these fields could propagate through space as waves. Waves that moved at a very specific speed. And when Maxwell calculated that speed, he found something remarkable. It matched the known speed of light. This wasn't just a coincidence. It suggested that light itself was an electromagnetic wave, a self-sustaining oscillation of electric and magnetic fields moving through space. And more importantly, it showed that the speed of light wasn't arbitrary. It was determined by the fundamental properties of those fields. In other words, the speed of light comes from the way the universe is built at a very basic level. It's woven into the relationship between electricity, magnetism, and space. So in that sense, light doesn't choose its speed. Its speed is defined by the structure of reality itself. But this still leaves an open question. Even if light has this built-in speed, why can't something else go faster? Why can't we simply take an object, give it more energy, and push it beyond that limit? This is where things take a more surprising turn. Because as you try to push something with mass closer and closer to the speed of a light, something unexpected happens. It becomes harder and harder to accelerate, not in a gradual, linear way, but in a way that grows more extreme the closer you get to that speed. It's almost as if the universe is gently resisting the attempt. But again, it's not resistance in the usual sense. There's no friction, no force pushing back in a simple way. Instead, what changes is the relationship between energy, motion, and time itself. As an object moves faster, its kinetic energy increases just as you would expect. But near the speed of light, that increase becomes enormous. To push an object even slightly closer to the speed of light requires more and more energy. And as you approach that limit, the required energy grows toward infinity, which means that, in practice, it becomes impossible. You would need an infinite amount of energy to reach the speed of light if you have any mass at all. And since infinite energy isn't something we can access, the limit remains out of reach. This isn't just a technical limitation, it's a fundamental one, a boundary that arises from the way energy and motion are connected. And it leads to an interesting conclusion. Light doesn't have mass. That's why it can move at this speed. Anything with mass is constrained by the energy required to accelerate it, so the speed of light becomes more than just the speed of light. It becomes the maximum speed at which anything without mass can travel, and by extension, the maximum speed at which anything can carry information across space. Because even if you could imagine something moving faster, there's another constraint waiting quietly behind this one. Information. When something happens, when one event influences another, that influence has to travel. And as far as we can tell, it cannot travel faster than light. This means that the speed of light is not just a limit on motion, but a limit on causality itself. A limit on how quickly cause and effect can propagate. And that's a very different kind of boundary. It's not just about how fast something moves, but about how the universe maintains a consistent order of events. If information could travel faster than light, it would be possible, at least in theory, to create situations where effects happen before their causes, where the sequence of events becomes scrambled, and that would break something very fundamental about how reality works. So the limit imposed by the speed of light acts as a kind of safeguard. a way of preserving the structure of cause and effect, a way of ensuring that events unfold in a consistent order. Now, all of this might sound a little abstract, but there's a simpler way to think about it. Instead of imagining light as something that is fast, imagine it as something that defines what fast even means. It's not just one example among many, it's the reference point, the upper boundary, the speed that everything else is measured against. And once you see it that way, the question we started with begins to change shape again. Because asking what the fastest thing in the universe is becomes less about finding a particular object, and more about understanding this limit, this constant, this built-in feature of reality. And the more you think about it, the more it starts to feel less like a coincidence, and more like a fundamental rule. Not something imposed from the outside, but something that arises naturally from the way space, time, and energy are connected. So light doesn't just happen to be fast, it is fast in the most complete sense. It moves at the maximum speed allowed by the universe, not because it is being pushed to that limit, but because that limit is part of what it is. At this point, it's almost impossible not to wonder, if light moves as fast as anything can possibly move, then what would happen if you tried to catch up to it? Not in a metaphorical sense, but literally. If you could build something fast enough, powerful enough, could you ever reach it? Could you move alongside a beam of light and watch it drift quietly beside you, as if it had finally slowed down? It's a simple idea, and yet it leads to one of the most surprising realizations in all of physics. Because the answer, gently but firmly, is no. Not only can you not go faster than light, you can't even quite reach it. And the reason for that isn't just a matter of engineering, or materials, or technological limits. It's something much deeper, woven into the way motion itself behaves at extreme speeds. But before we step into that, it helps to start somewhere more familiar. Imagine you're running. At first, increasing your speed is straightforward. You push harder, your legs move faster, and your speed increases in a way that feels natural and predictable. If you double your effort, you might not double your speed exactly, but you get a sense that more energy leads to more motion. Now imagine upgrading that situation. Instead of running, you're in a car. Press the accelerator and the car speeds up. More fuel, more power, more speed. The relationship still feels intuitive. Add energy, get more velocity. This pattern holds for almost everything we experience in daily life. Push harder, go faster. So it's tempting to assume that this trend continues indefinitely. That if you keep adding energy, you can keep increasing speed without any real limit. But the universe, as it turns out, doesn't quite agree with that assumption. Let's imagine a thought experiment. Suppose you had a spacecraft, something far beyond our current technology, capable of accelerating continuously for a very long time. At first, everything behaves as expected. As the engines fire, the ship gains speed, faster and faster, gradually approaching extraordinary velocities. At some point, you begin to notice something subtle. Each additional burst of energy seems to have a slightly smaller effect. You're still accelerating, but not as quickly as before. It takes more effort to achieve the same increase in speed. This isn't something you would notice at low speeds. It only becomes significant when you start approaching a very particular threshold, the speed of light. As you get closer and closer to that speed, the pattern becomes more extreme. You add more energy, and your speed increases, but only by a tiny amount. Add even more energy, and the increase becomes even smaller. It's as if the speed is resisting you, not by pushing back, but by becoming harder and harder to approach. And eventually you reach a point where the required energy to go any faster grows beyond anything you could realistically provide. It doesn't matter how powerful your engines are or how long you keep accelerating. The closer you get to the speed of light, the more the rules themselves begin to change, and this is where intuition starts to fall away. Because what's changing isn't just your speed, it's the relationship between energy and motion. In everyday life, energy and speed are closely linked in a relatively simple way. But near the speed of light, that relationship becomes highly nonlinear. The energy required to keep accelerating doesn't just increase steadily, it grows dramatically, approaching infinity as you get closer to that limit, which means that reaching the speed of light would require an infinite amount of energy. And since that's not something we can access, the limit remains out of reach. But there's another way to look at this, one that feels a bit more intuitive. Instead of thinking about light as something you're trying to catch, imagine it as something that always stays just ahead of you. No matter how fast you go, light always moves away at the same speed. If you accelerate, it doesn't slow down relative to you. It doesn't adjust its pace. It simply continues, unchanged, maintaining that same constant speed. This is very different from how most things behave. If you throw a ball while moving forward, the ball's speed adds to your own. To someone standing still, it moves faster than if you had thrown it while standing still. But light doesn't follow that rule. Its speed doesn't depend on your motion, and that's where the deeper implications begin to appear. Because if light's speed is always the same, no matter how you move, then something else has to adjust to make that possible. Space, time, or both. This is the point where our everyday understanding starts to feel a little less stable, because we're used to thinking of space and time as fixed, stable, independent of motion. But near the speed of light, those assumptions begin to shift. Distances can change, time can behave differently, and all of this happens in a way that ensures one thing remains constant: the speed of light. So when we ask whether anything can go faster than light, we're not just asking about speed, we're asking about the structure of reality itself. Could something exceed that limit? In theory, you might imagine it. You might picture an object moving so quickly that it overtakes light, racing ahead into the darkness. But if that were possible, it would lead to consequences that go far beyond simple motion. It would begin to affect cause and effect. Because if something could travel faster than light, it could, under certain conditions, appear to arrive before it was sent. Messages could be received before they were transmitted, events could influence the past, and that introduces a kind of instability into the structure of reality, a breakdown in the order of events. So the speed of light acts as more than just a limit on motion. It acts as a boundary that preserves the sequence of cause and effect, a kind of quiet rule that ensures events unfold in a consistent direction. Now, there are a few ideas that seem to challenge this. Concepts that sound, at least on the surface, like they might allow for faster-than-light travel. Things like hypothetical particles called tachyons, or shortcuts through space known as wormholes. But these ideas remain speculative. Tachyons, if they exist at all, would behave in ways that don't align with anything we've observed, and wormholes, while mathematically possible in some models, would require conditions and materials that we don't currently know how to create or sustain. So for now, they remain interesting possibilities rather than practical realities. What we do know with a high degree of confidence is that nothing with mass can be accelerated to the speed of light, let alone beyond it, and that light itself doesn't need to accelerate. It simply moves at that speed, always. So chasing light becomes a kind of asymptotic journey. You can get closer and closer, but you never quite arrive, and there's something quietly elegant about that. Because it means that the fastest thing in the universe is not just fast in a relative sense, it's fast in an absolute sense. It defines the upper boundary of motion, a limit that shapes everything else. The question becomes unavoidable. If light always moves at the same speed no matter how you chase it, no matter how fast you go, then something about our usual way of thinking must be incomplete. Because in everyday life, speeds add together. If you walk forward on a moving train and toss a ball ahead of you, the ball moves faster relative to the ground than it would if you had thrown it while standing still. Motion stacks, velocities combine. That's how the world appears to work. So naturally you might expect that if you were moving fast enough and you shone a beam of light forward, that light would move just a little bit faster than usual, at least from someone else's perspective. but experiment after experiment suggested something different. The speed of light didn't change, not when the source moved, not when the observer moved, not when the measurement was repeated under different conditions. It remained stubbornly constant, as if it were ignoring the usual rules. And this is where things began to feel less like a small puzzle and more like a deep inconsistency. Because if the speed of light is always the same, then either our understanding of motion is wrong, or our understanding of space and time is incomplete. And for a while, scientists tried to hold on to both. They searched for something that might explain this behavior without rewriting the foundations of physics. One idea was that light traveled through a kind of invisible medium, sometimes called the ether, which would act as a universal reference frame. If that were true, then the speed of light might only appear constant because we were always measuring it relative to this hidden background. It was a reasonable idea. But when experiments were designed to detect this ether, to measure Earth's motion through it, the results came back empty. Nothing. No drift. No variation. No sign that such a medium existed. And so the problem remained. How can the speed of light be the same for everyone, regardless of how they're moving? It's a deceptively simple question, but answering it required letting go of something very familiar, something we tend to take for granted, the idea that time is the same for everyone. In the early 20th century, a young physicist named Albert Einstein approached this problem from a different angle. Instead of trying to explain why the speed of light might vary, he asked a more radical question. What if it doesn't? What if the speed of a light is truly constant for all observers, no matter how they move? And if that's true, what would have to change to make it possible? It's a simple shift in perspective, but it leads to consequences that are anything but simple. Because if the speed of light is fixed, then something else has to give, and the only things left are space and time themselves. To get a feel for this, imagine two observers. One is standing still on the ground, the other is moving past them at a very high speed. Both of them shine a beam of light forward. From the perspective of the person on the ground, you might expect the moving observer's light to travel faster, since it's being emitted from something already in motion. But that's not what happens. Both observers measure the light moving at exactly the same speed, which means that their measurements of distance and time cannot be the same. Something must adjust so that both of them arrive at the same result, and that something turns out to be both distance and time. This is the heart of what became known as special relativity, a theory that doesn't just describe motion, but reshapes the way we understand reality at high speeds. In this framework, space and time are not fixed and separate. They are flexible. They can stretch, contract, and shift depending on how you move. And all of this happens in a way that keeps the speed of light constant. Now, this might sound abstract, but it can be understood with a few simple ideas. First, time is not the same for everyone. If you're moving very quickly relative to someone else, your time will pass more slowly compared to theirs. This isn't something you would notice in everyday life, because the effect is extremely small at ordinary speeds. But as you approach the speed of light, it becomes more significant. Your clock ticks more slowly. Your processes take longer. From your perspective, everything feels normal, but from someone else's point of view, you appear to be experiencing time at a different rate. Second, distances can change. If you're moving at very high speeds, the distance you measure in the direction of motion becomes shorter compared to someone who is standing still. Again, this effect is tiny at low speeds, but it grows as you approach the speed of light. So both time and space adjust themselves, just enough to ensure that the speed of light remains the same for all observers. And this leads to a remarkable conclusion. The speed of light is not just a property of light. It is a fundamental feature of space and time, a constant that defines how the two are connected. And because of that, it acts as a kind of cosmic speed limit, not imposed by a force, not enforced by a barrier you can crash into, but built into the geometry of reality itself. Nothing with mass can reach or exceed this speed. because doing so would require space and time to behave in ways that are not physically possible. It would require infinite energy, infinite distortion, a breakdown of the relationships that keep the universe consistent. So instead, everything with mass is confined to speeds below this limit, always able to approach it, but never quite reach it. Light, on the other hand, exists exactly at that boundary. It doesn't accelerate to get there, it simply is there. And this creates a kind of dividing line. On one side, everything with mass moving at speeds less than light, experiencing time in a way that can vary depending on motion. On the other side, light itself, moving at this constant speed, unaffected by the usual rules that apply to objects with mass. And this distinction has consequences that reach far beyond simple motion. Because once you accept that time can change depending on speed, the entire structure of cause and effect becomes more delicate. Events that appear simultaneous to one observer may not be simultaneous to another. The order of events can depend on your frame of reference. But through all of this, one thing remains consistent. No information can travel faster than light. No signal, no influence, no cause. And that ensures that even though time and space can shift, the underlying order of events is preserved. The universe remains coherent. So when we talk about the speed of light as a limit, we're not just talking about speed in the usual sense, we're talking about the maximum rate at which anything can influence anything else. The fastest possible connection between cause and effect. And once you begin to see it that way, the question we started with changes again, just slightly. Because we're no longer just asking what is the fastest thing. We're beginning to understand why there is a fastest thing at all. A limit that doesn't come from technology or material constraints, but from the way space and time are structured. There's a point, somewhere between the speeds we're comfortable imagining and the speeds the universe quietly allows, where things begin to behave in ways that feel slightly unfamiliar. Not dramatically at first, not in a way you'd immediately notice if you were simply going about your day. But gradually, as speed increases, the rules that once felt solid begin to shift, just enough to make you pause and reconsider what motion really means. Up to now, we've treated speed as something straightforward. Faster means covering more distance in less time, add energy, gain velocity, a simple, almost reassuring relationship. But as something moves closer and closer to the speed of light, that simplicity starts to dissolve. Let's imagine gently that you're inside a spacecraft. Not something noisy or chaotic, but something smooth, controlled, steadily accelerating through space. There are no windows showing stars streaking past dramatically, no sudden jolts. Just a quiet, continuous increase in speed. At first, everything behaves exactly as you'd expect. You feel the acceleration. Your body presses slightly into your seat. Objects inside the spacecraft respond normally. A dropped item falls to the floor. A clock ticks steadily on the wall. From your perspective, nothing unusual is happening. But far away, from the point of view of someone watching your journey, something subtle has already begun to change. Your time is no longer matching theirs. This is where the idea of time dilation quietly enters the picture. It's not something you would feel directly. Your own experience of time remains perfectly normal. Your heartbeat, your thoughts, your sense of duration, all of it continues as it always has. But to an outside observer, your clock appears to be ticking more slowly. At first, the difference is tiny, almost impossible to detect without extremely precise instruments. But as your speed increases, the effect becomes more noticeable. The faster you go, the slower your time appears to pass relative to someone who is not moving as quickly. It's not an illusion. It's not a trick of perception. It's a real, measurable difference, and it applies to everything. Your clock, your body, even the processes inside your cells. From your perspective, nothing has changed, but from theirs, everything about you has slowed down. Now let's pause for a moment and sit with that. Because it's one of those ideas that sounds simple at first, but becomes more surprising the longer you think about it. Time is not absolute. It doesn't flow at the same rate for everyone. It depends on how you move, and as you approach the speed of light, that dependence becomes stronger and stronger. Now, there's another effect unfolding at the same time. While your time is slowing down relative to an outside observer, the distances in front of you begin to change as well. Specifically, they begin to contract. From your perspective inside the spacecraft, the distance to your destination appears shorter than it would to someone standing still. It's not that space is physically compressing in a way you can feel, but the way distances are measured shifts depending on your motion. So as your speed increases, the journey ahead becomes, in a sense, more manageable. Less distance to cover, less time required from your perspective. And this leads to an interesting balance. From the outside, your journey takes longer. Your clock runs slowly. But from your own point of view, the distance shrinks, and your experience of the trip remains relatively brief. Two different perspectives, both valid, both describing the same event but in very different ways. And this is one of the defining features of motion at extreme speeds. There is no single, universal description that everyone agrees on. Each observer measures time and distance according to their own frame of reference, and yet all of these measurements remain consistent with the underlying rules. Now, let's return to the idea of acceleration. As your spacecraft continues to speed up, you're pouring more and more energy into the system. At lower speeds, this translates into clear increases in velocity. But as you approach the speed of light, something changes. The same amount of added energy produces a smaller increase in speed than it did before, and this effect grows stronger with each step. You add energy, and your speed increases, but by less than it did previously. Add even more, and the increase becomes smaller still. It's as if your speed is approaching a boundary, getting closer and closer, but never quite reaching it. And this is where the concept of relativistic mass often enters the conversation. As an object moves faster, its resistance to further acceleration increases, not because its actual mass is changing in a simple, everyday sense, but because the relationship between energy and motion is shifting. The faster you go, the more energy is required to keep accelerating, and near the speed of light, that requirement becomes extreme. So extreme, in fact, that reaching the speed of light would require an infinite amount of energy, which means it cannot happen, not for anything with mass. Now, there's another layer to this, one that's perhaps even more intriguing. As your speed increases, your view of the universe begins to change. Light itself, the very thing that defines the speed limit, behaves differently depending on your motion. From your perspective, the light in front of you becomes compressed, shifting toward higher energies. Light behind you stretches out, moving toward lower energies. The entire visual field begins to distort in subtle ways. The direction you're moving toward becomes brighter, more concentrated, while everything behind you fades. It's not something you would experience in everyday life, but it's a natural consequence of moving at extreme speeds. Even the way you perceive the passage of time in the universe around you would begin to shift. Events that seem distant and slow from one perspective might appear closer and faster from another. And all of this is happening not because the universe itself is changing, but because your relationship to it is. Your motion is altering the way space and time are measured. Now, it's worth noting that these effects are not limited to thought experiments. They've been observed. Particles accelerated to high speeds in laboratories exhibit time dilation. Their lifetimes increase when they move faster, allowing them to persist longer than they would at rest. Clocks on fast-moving aircraft or satellites tick at slightly different rates compared to those on the ground. These differences are small but measurable, and they confirm that what we're describing is not just theoretical. It's part of the real behavior of the universe. So as you approach the speed of light, several things are happening at once. Time slows down relative to others. Distances contract in the direction of motion. Energy requirements increase dramatically. And your perception of the surrounding universe begins to shift. All of these effects work together to enforce that one central rule. Nothing with mass can reach the speed of light. You can get closer and closer, but the final step remains out of reach. And there's something quietly consistent about that, because it means the speed of light isn't just a number, it's a boundary where the relationships between space, time, and energy reach their limits, a point beyond which the usual rules no longer apply. Long before equations enter the picture, there's a simple expectation we all quietly rely on. Events happen in an order. You press a switch, and then the light turns on. You drop something, and then it falls. You speak, and then someone hears you, because comes first, effect follows. It feels so obvious that we rarely stop to think about it. But this simple ordering is not just a habit of thought. It's something the universe carefully preserves, and the speed of light plays a central role in keeping that order intact. Because once you begin to imagine something travelling faster than light, even just as a thought experiment, that neat sequence of cause and effect begins to loosen in ways that are surprisingly difficult to manage. Let's take a step into that idea slowly. Imagine you have a way of sending a message not at the speed of light, but faster than it. Something instantaneous, or at least quicker than anything light could carry. At first, this sounds convenient. You could communicate across vast distances without delay, send a signal from one side of the planet to the other instantly, reach across space without waiting minutes, hours, or years for a reply. It feels like an upgrade. But now, consider this. Because of the way motion works in the universe, two observers moving relative to each other do not always agree on the timing of events. We touched on this earlier, the idea that what looks simultaneous to one observer may not be simultaneous to another. This effect is small at everyday speeds, but it becomes significant as speeds increase. So imagine two observers, far apart, moving relative to one another. From the perspective of one observer, you send a faster-than-light message at a certain moment. The signal travels and arrives at the other observer almost instantly, faster than light would allow. So far, nothing seems too unusual. But now shift perspective. From the point of view of the second observer, because of the way time and space are measured differently in their frame of reference, the timing of those same events can appear reversed. To them, it can look as though the message arrived before it was sent, not by a small margin, but in a way that breaks the usual sequence. Effect before cause. And that's where things start to unravel. Because if one observer can receive a message before it was sent, then in principle, they could respond immediately, sending a reply back, also faster than light. And depending on the relative motion between the two observers, that reply could reach the original sender before they even decided to send the first message, which creates a loop, a message that arrives before it exists, a response to a question that hasn't been asked yet. Now, this might sound like something out of a science fiction story, but it's a natural consequence of combining faster-than-light travel with the way relativity handles time, and it leads to a problem, a very fundamental one, because once cause and effect can be rearranged, the universe loses its consistency. Imagine trying to build any kind of reliable sequence of events in a world where outcomes can influence their own origins, where a message can prevent itself from being sent, where an action can undo the reason it was taken in the first place. This isn't just confusing, it's logically unstable. The structure of events would become tangled, with no clear direction, no consistent ordering. And this is why the speed of light acts as a boundary, not just for motion, but for information. It ensures that signals cannot travel in a way that would disrupt the sequence of cause and effect. No matter how observers move, no matter how their measurements of time and space differ, the order of causally connected events remains intact, cause always comes before effect. Not because it feels right, but because the rules of the universe enforce it. Now, there's another way to look at this, one that feels a bit more grounded. Instead of thinking about messages and observers, think about influence. For one event to affect another, something must travel between them. energy, information, a signal of some kind. That connection takes time, and the speed of light defines the maximum rate at which that connection can occur. So the universe can be thought of as a network of events, each one linked to others by these signals, and the speed of light sets the pace at which those links can form. If you try to exceed that pace, the connections begin to overlap in ways that no longer make sense. Events start to interact with parts of the timeline they shouldn't be able to reach, and the structure of the network breaks down. Now, it's worth noting that the universe doesn't present this as a visible barrier. There's no wall, no edge, no sudden stop. Instead, the rules are built into the way space and time behave. As you approach the speed of light, the effects we talked about earlier, time dilation, length contraction, the increasing energy required to accelerate, all of these work together to prevent you from crossing that boundary. It's not a force pushing you back. It's the system itself adjusting so that the limit is never reached. And that's what makes it feel so different from everyday limits. A speed limit on a road is something you can choose to ignore, at least for a while. It's an external rule enforced by consequences, but the speed of light is not like that. It's not something you can break. It's something that defines what breaking would even mean. Now there are, of course, ideas that explore what might happen if this rule could be bypassed. We mentioned a few earlier: wormholes, exotic forms of matter, theoretical constructs that allow for shortcuts through space. These ideas often try to avoid faster than light travel by bending space itself, rather than moving through it in the usual way, and in doing so they attempt to preserve the underlying rule. Because even in these speculative scenarios, the need to maintain causality remains. Any model that allows for faster-than-light effects must somehow prevent paradoxes or accept them as a consequence. And most of our current understanding leans strongly toward the idea that the universe does not permit such inconsistencies, that the rule holds. So when we say that nothing can travel faster than light, we're not just describing a physical limitation, we're describing a safeguard, a principle that keeps the universe coherent, a way of ensuring that events unfold in a consistent, understandable order. And once you see it that way, the speed of light becomes something more than just a number. It becomes a kind of organizing principle, a boundary that shapes how everything connects. Now, this might leave you with an interesting thought. If faster-than-light travel breaks the rules in such fundamental ways, are there situations where things appear to go faster than light, without actually violating those rules? Because sometimes, under certain conditions, motion can look like it exceeds that limit, even though it doesn't in a strict sense. Not everything in the universe is content to move at the comfortable speeds we experience in daily life. Some things get very close to that upper boundary, close enough that the difference between their speed and the speed of light becomes almost difficult to describe in ordinary terms. Close enough that the rules we've been discussing, the ones about time slowing down and energy requirements increasing, are no longer subtle effects but dominant ones. And these aren't hypothetical objects. They're real. They exist all around us, quietly, constantly, often without us ever noticing. To begin with, it helps to think small, much smaller than anything we can see, because the objects that come closest to the speed of light are not cars or planes, or even spacecraft. They're tiny particles, some of the smallest building blocks of matter, moving through space with enormous energy. One of the most familiar examples is the electron. Electrons are everywhere. They're part of every atom, part of everything around you. And under normal conditions, they move in ways that are relatively modest compared to the cosmic scale we've been building toward. But when electrons are accelerated, either naturally in space or artificially in laboratories, they can reach speeds that are astonishingly close to the speed of light. Not quite there, but very, very close. So close that if you tried to measure the difference directly, you'd find yourself dealing with tiny fractions, differences that require precise instruments and careful calculations to even notice. Now, there are natural processes that create these high-speed particles, for example, cosmic rays, These are particles, often protons or atomic nuclei, that travel through space at extremely high speeds. They originate from energetic events like supernova explosions or other violent processes in the universe, and they carry with them enormous amounts of energy. When these particles reach Earth, they collide with atoms in the atmosphere, creating cascades of secondary particles that spread out and continue downward. Among these secondary particles are things called muons. Muons are similar to electrons but heavier, and they have an interesting property. They're unstable. If you were to create a muon at rest, it would decay into other particles very quickly, in a fraction of a second. So quickly, in fact, that if you produced them high in the atmosphere, you might expect them to decay long before they could reach the surface of the Earth. And yet, they do reach the surface, in large numbers. This is one of the most elegant real-world demonstrations of what happens at speeds close to light. Because these muons are moving so fast, their internal clocks, from our perspective, are running more slowly. Time dilation. From the muon's point of view, its lifetime hasn't changed. It still exists for the same duration. But from our perspective, that duration is stretched, which means it survives long enough to travel much farther than it otherwise would. And so, particles created high in the atmosphere manage to reach the ground, even though, according to everyday expectations, they shouldn't. It's a quiet confirmation of the ideas we've been exploring. Now, beyond natural processes, humans have also learned how to accelerate particles to incredible speeds. Particle accelerators are machines designed to do exactly this. They use electric and magnetic fields to push particles faster and faster, guiding them along carefully controlled paths, often in circular tracks. One of the most well-known examples is the Large Hadron Collider. Inside this massive structure, particles are accelerated to speeds that are extremely close to the speed of light. Not equal to it, but so close that the difference becomes almost negligible in everyday terms. For instance, a proton in such an accelerator might be moving at 99.999999% of the speed of light. That remaining fraction, tiny as it is, still represents a boundary that cannot be crossed. And reaching even that level requires enormous amounts of energy. This is where the earlier idea becomes very tangible. As particles get closer to the speed of light, adding more energy doesn't significantly increase their speed. Instead, that energy goes into increasing their momentum in a way that doesn't translate into simple acceleration. They're already so close to the limit that pushing further becomes increasingly difficult. And this is why particle accelerators focus not just on speed, but on energy. The particles inside them carry immense energy, even though their speed is only slightly below that ultimate limit. Now, there's something else worth noticing here. From our perspective, these particles are moving at incredible speeds. But from the particle's own point of view, things look very different. Distances in the direction of motion appear contracted. The journey they're taking seems shorter. So while we see them travelling vast distances at high speed, from their perspective, the distance is reduced, allowing them to complete the journey within their limited lifetime. Again, two perspectives, both valid, both consistent with the same underlying rules. Now, all of this might raise an interesting thought. If particles can get so close to the speed of light, does it really matter that they can't quite reach it? Is that last tiny fraction significant? And the answer quietly is yes. Because that final step is not just another increment. It represents a fundamental boundary. Crossing it would require the rules themselves to change. So no matter how much energy you add, no matter how advanced your technology becomes, anything with mass will always remain just below that speed, always approaching, never arriving. And yet there's something almost poetic about that, because it means the universe allows for motion that is incredibly fast, almost indistinguishable from the maximum, while still preserving the structure that keeps everything consistent. Speed, when it belongs to nature, has a way of feeling distant. Particles racing through space, light crossing unimaginable distances, cosmic events unfolding far beyond our reach. All of it sits slightly outside our everyday experience. We can understand it, measure it, even describe it with surprising accuracy, but it doesn't quite feel personal. What changes things just a little is when we try to build that speed ourselves. Because the moment humans attempt to create something fast, truly fast, the abstract becomes tangible. It becomes engineering, effort, limitation, and, in a quiet way, ambition. So instead of looking outward for a moment, it helps to turn inward and ask a different version of the question. How fast have we actually managed to go? Not in theory, not in equations, but in reality. And the answer, like most things in this story, depends on what you mean by we. Let's start with something familiar. Machines. The fastest vehicles ever built. For a long time, speed records were grounded firmly on Earth. Cars, trains, experimental vehicles designed to push against air resistance and mechanical limits. Over time, these speeds crept upward, from tens of kilometers per hour to hundreds, then beyond. Supersonic aircraft broke the sound barrier, then exceeded it many times over. Experimental jets reached speeds of several thousand kilometers per hour, cutting through the atmosphere in ways that would have seemed impossible just decades earlier. And yet, even at those speeds, impressive as they are, we're still operating within a very narrow band compared to the larger scale we've been exploring. A jet travelling at Mach 3 or Mach 5 feels extraordinary from a human perspective. But in terms of the speed of light, it's barely moving. Now move beyond the atmosphere. Once we leave the constraints of air resistance, a different kind of speed becomes possible. Spacecraft. When rockets first began to reach orbit, the required speeds were already significant. To remain in orbit around Earth, a spacecraft needs to travel at about 28,000 kilometers per hour. That's fast enough that, from the ground, it appears to circle the planet in just over an hour. But even that is only the beginning. To leave Earth's gravitational pull entirely, to escape into deeper space, a spacecraft must reach escape velocity, roughly 40,000 kilometers per hour, and once it's free from Earth, it can begin to gain speed in more creative ways. Some spacecraft use what's called a gravity assist, or slingshot maneuver. They pass close to a planet, using its gravity to accelerate, effectively borrowing a small amount of the planet's orbital momentum. It's a clever technique. Instead of relying solely on fuel, the spacecraft uses the motion of massive bodies to increase its own speed. And through a series of these maneuvers, spacecraft can reach speeds far beyond what their engines alone could provide. One of the most notable examples is the Parker Solar Probe. This spacecraft, designed to study the Sun up close, has achieved speeds of over 600,000 kilometers per hour. That's roughly 170 kilometers per second, an extraordinary number. At that speed, it could travel from one side of the Earth to the other in under a minute. And yet, even here, even at what might feel like an almost unimaginable pace, we are still far below the speed of light. Light travels at about 300,000 kilometers per second. So even our fastest spacecraft, moving at hundreds of kilometers per second, are still only reaching a small fraction of that ultimate limit. Now, let's shift from large machines to something much smaller. Because when it comes to the fastest things we've ever built, the real champions are not spacecraft or rockets, they're particles. Inside particle accelerators, humans have managed to push tiny particles to speeds that come astonishingly close to the speed of light. Take the Large Hadron Collider, for example. Within its circular tunnels, protons are accelerated to speeds exceeding 99.999999% of the speed of light. That's so close to the limit that the difference becomes almost difficult to express in everyday terms. If light were running a race around the Earth, these protons would finish just fractions of a second behind, even after circling the planet multiple times. And reaching those speeds is no small task. It requires enormous amounts of energy, powerful electromagnetic fields, and precise control over the particles' paths. But even with all of that, there is still a boundary. No matter how much energy is added, those particles never quite reach the speed of light. They approach it, asymptotically, getting closer and closer, but never crossing that final gap. And that gap, however small it appears, represents something fundamental. It's not just a technical limitation, it's a built-in rule. Now there's something quietly interesting about this, because when we talk about the fastest things we've ever built, we're really talking about two very different categories. Large objects like spacecraft which move quickly but remain far from the ultimate limit, and tiny particles which can approach that limit extremely closely, but only because they have so little mass. And this difference matters, because mass is what makes reaching the speed of light so difficult. The more mass something has, the more energy is required to accelerate it, especially as it gets closer to that limit. So while it's possible to push tiny particles to near-light speeds, doing the same for something large like a spacecraft carrying people becomes vastly more challenging. The energy requirements would be enormous, beyond anything we currently have the ability to produce. Now, this leads to an interesting reflection. When we think about speed in human terms, we tend to imagine larger things moving faster. Bigger engines, more power, greater momentum. But at the extreme end of the scale, the opposite becomes true. The smallest things can go the fastest, because they require less energy to accelerate, because they can approach that boundary without the same constraints. And this flips our intuition in a subtle way. It suggests that the fastest motion in the universe is not something grand or massive, but something tiny, almost invisible, moving quietly at the edge of what's possible. Now, there's another layer to this. Because even though we've built machines that can accelerate particles to incredible speeds, we don't actually use those speeds for travel in the usual sense. A proton in a particle accelerator isn't going anywhere meaningful. It's moving in a controlled loop, guided by magnetic fields, its motion carefully managed for experiments. So while it is technically one of the fastest things we've ever created, it doesn't carry us across space. It doesn't take us from one place to another. And this highlights a gap between what is physically possible and what is practically useful. We can achieve extreme speeds in controlled environments, but translating that into large-scale motion, moving people or objects across vast distances, is a very different challenge. One that brings us back to the limits imposed by energy, mass, and the structure of space-time itself. Still, there's something quietly remarkable about what we've managed to do. From the earliest vehicles moving at walking speed to particles racing just below the speed of light, the range of motion we've explored is vast, and each step along that path has expanded our understanding, not just of how to move faster, but of what speed actually means. Now, as we continue, it's worth keeping one thought in mind. Even though we've built incredibly fast things, none of them have broken the fundamental limit. None have exceeded the speed of light. There's a moment, usually right around here, where things begin to feel slightly contradictory. Up until now, one idea has been repeated quietly but consistently. Light travels at a constant speed. The same for everyone. The same everywhere. A kind of steady anchor in a universe where so many other things depend on perspective. And then, almost immediately, you run into a situation that seems to say the opposite. Light slows down. At least, that's how it appears. If you shine a beam of light through air, it moves extremely fast. Through water, it moves more slowly. Through glass, slower still. Anyone who has ever looked at a straw in a glass of water has seen the bending of light, the way it shifts direction as it passes from one medium to another. And behind that bending is a change in speed. So now we have two ideas sitting side by side. Light always travels at the same speed, and light can slow down. Both of them seem true. So which one is it? To untangle this, it helps to slow down just a little and look carefully at what's actually happening when we say that light is slowing down. Because in everyday language, that phrase makes sense. It's intuitive. Something enters a denser material, and it moves more slowly through it. But the deeper explanation is a bit more subtle. Imagine a beam of light travelling through empty space. There's nothing in its way. No atoms, no particles, no structure to interact with. It simply moves, uninterrupted at its natural speed. Now imagine that same beam entering a piece of glass. Glass is not empty, it's made of atoms, arranged in a structured way. And as light moves through it, it doesn't just pass cleanly from one side to the other. Instead, it interacts, very quickly, very subtly, but continuously. The electromagnetic wave that makes up light encounters electrons in the material. These electrons respond, oscillate, and in doing so, they effectively absorb and re-emit the light's energy in a coordinated way. This process happens incredibly fast. So fast that it feels continuous. But what it means is that the light is not simply moving freely through the material, it's being delayed, very slightly, at each interaction. And when you add up all of those tiny delays across the entire path, the overall effect is that the light takes longer to pass through the material than it would have in empty space. So from the outside, it looks like the light has slowed down. But in a deeper sense, something else is happening. Between each interaction, the light is still moving at its usual speed. It's just not moving continuously. It's pausing in a way at each step, and those pauses add up. This distinction might feel subtle, but it's important, because it preserves the idea that light itself always travels at the same fundamental speed. What changes is the path it takes, and the interactions it undergoes along the way. Now there's another interesting effect that comes from this. Because when light enters a material and slows down in this effective sense, it also changes direction. This is what we see as refraction. Light bends when it moves from one medium to another. For example, when light passes from air into water, it slows down slightly, and its path bends toward the normal, the line perpendicular to the surface. This bending is what makes objects underwater appear shifted from where they actually are. It's also what allows lenses to focus light, creating images in cameras, telescopes, and even your own eyes. So the slowing of light in a medium is not just a curiosity, it has practical consequences. It shapes how we see the world. But it still raises that original question. If light can appear to move more slowly in materials, does that mean the speed of light isn't really constant? And the answer, carefully stated, is this. The speed of light in a vacuum is constant. That's the key. In empty space, where there are no interactions to delay it, light always travels at the same speed. And it's this vacuum speed that defines the cosmic limit. The maximum speed at which anything can travel, the maximum speed at which information can propagate. Everything else, light in air, light in water, light in glass, is a variation on that theme, a result of interactions with matter, not a change in the underlying rule. Now, there's a slightly more surprising twist to this. In certain very specific conditions, scientists have been able to create situations where light appears to slow down dramatically. Not just a little, but by large factors. In carefully controlled experiments, light has been slowed to a crawl, even to speeds where it moves just a few meters per second. And in some cases it has even been brought to a temporary stop. That sounds almost impossible at first. How can the fastest thing in the universe be slowed to walking speed, or stopped entirely? But again, the explanation lies in interactions. In these experiments, light is passed through specially prepared materials, often at extremely low temperatures, where the behavior of atoms becomes highly coordinated. The light interacts with the material in such a way that its energy is effectively stored and then released again. So what we're seeing is not light moving slowly in the usual sense, but light being absorbed and re-emitted in a controlled way that mimics slow motion. It's a bit like a message being passed along a chain of people. The message itself moves quickly from person to person, but if each person pauses briefly before passing it on, the overall progress slows down. The underlying speed hasn't changed, but the process has. Now all of this might seem like a contradiction at first. Light is constant. Light can slow down. Light can even appear to stop. But once you separate the idea of light's fundamental speed from the way it interacts with matter, the picture becomes clearer. The constant speed of light applies in a vacuum in the absence of interactions. In materials, what we observe is the combined effect of light's motion and its interactions with the medium. And those interactions can alter the effective speed in ways that are both useful and, at times, surprising. So when we ask whether light is always the same speed, the answer depends on how we're asking the question. If we're talking about its fundamental role in the structure of space-time, then yes, it is constant, unchanging, a fixed point in the universe's rulebook. But if we're talking about how it behaves in the environments we encounter, then the story becomes more nuanced, because light is not isolated. It moves through matter, interacts with it, and in doing so, reveals layers of behaviour that go beyond simple motion. And this brings us back once again to the idea of limits, because even though light can appear to slow down in materials, nothing in those processes allows information to travel faster than its speed in a vacuum. That boundary remains intact, unbroken. From time to time, the universe allows something that looks like a violation. Not in the sense of actually breaking its rules, but in the way an event can appear, at least for a moment, to step just outside of what we expect. And if you're not looking carefully, if you take that appearance at face value, it can seem like something has moved faster than light, which by now should feel slightly suspicious, because we've spent quite a bit of time building up the idea that nothing actually does that. So how can something look like it does? To begin with, it helps to remember something simple, but easy to overlook. What we see is not always a direct picture of what's happening, it's a reconstruction. Light leaves an object, travels through space and reaches your eyes. Your brain processes that information and presents it to you as a continuous experience. But that experience depends on timing, distance, and perspective. And when those factors align in certain ways, they can create illusions that feel surprisingly convincing. Let's start with something familiar, something you've probably noticed without giving it much thought. Imagine you're standing at night, watching a distant airplane cross the sky. Its lights blink steadily as it moves from one side of your view to the other. It looks smooth, continuous, predictable. Now imagine instead that you're holding a laser pointer and you sweep it across a distant wall. The spot of light moves across the surface. If the wall is close, the motion is slow and easy to follow. But if the wall is very far away and you move your hand even slightly, the spot can move incredibly fast across the surface. In fact, if the wall were far enough and you swept your hand quickly enough, that spot could appear to move faster than light. Now, this might sound like a contradiction, but it isn't. Because the spot of light is not a single object travelling from one point to another, it's a sequence. Each point on the wall is being illuminated by a different beam of light at a different moment. The light itself is still travelling at its usual speed, but the pattern of illumination moves across the surface much more quickly. There's no single thing moving across that wall faster than light. It just looks that way. And this is the key idea behind many apparent faster-than-light motions. The difference between something physically travelling and something appearing to move due to the timing of a light reaching us. Now let's take this idea and move it into space, because there are real astronomical observations where objects seem to move faster than light. One of the most striking examples involves jets of material ejected from certain types of galaxies, particularly those with active centres. These jets can extend for enormous distances, and when we observe them from Earth, parts of the jet can appear to move across the sky at speeds greater than light, which sounds at first like a direct contradiction. But again, the explanation lies in perspective. Imagine a jet of material moving almost directly toward you, but at a slight angle. It's moving very fast, close to the speed of light, but not exceeding it. As it travels, it emits light continuously. That light takes time to reach you. But because the jet is moving toward you, each new bit of light has a slightly shorter distance to travel than the previous one, so the light from later positions catches up, in a sense, with the light from earlier positions. When you observe this sequence from a distance, the timing gets compressed. Events that happened over a longer period of time appear closer together, and when you translate that compressed timing into motion across the sky, it can look as though the object is moving faster than light, but it isn't. The actual motion is still below the speed of light. It's the way the light reaches you, and the way your brain reconstructs that motion, that creates the illusion. Now there's something quietly important about this, because it shows that even though the speed of light is a strict limit, our observations can sometimes make it look like that limit has been exceeded. And this can be confusing if we don't take into account how information travels, because what we're always observing is not the object itself, but the light carrying information about that object, and that light has its own travel time, its own delays, its own geometry. So when objects move in certain directions at certain speeds, the timing of the light can distort the way we perceive their motion. Now, there's another kind of apparent faster-than-light effect that comes from shadows. Imagine a large object casting a shadow on a distant surface. If the object moves, the shadow moves too. And if the surface is far enough away, a small movement of the object can cause the shadow to sweep across the surface very quickly, in some cases faster than light. But again, the shadow is not a physical object. It doesn't carry energy or information in the same way. It's simply the absence of light, a pattern. And patterns can move in ways that don't correspond to the motion of a single object. Now, this distinction between objects and patterns becomes very important, because the universe doesn't forbid patterns from appearing to move quickly. What it limits is the motion of physical objects and the transmission of information. Nothing that carries information from one place to another can exceed the speed of light. And that's the boundary that matters. So when we see something that appears to move faster than light, we have to ask a careful question. Is something actually travelling from one point to another at that speed? Or is it a sequence of events, a pattern, a projection created by the timing of light? And in every case we've observed, the answer has been the latter. The rules are not being broken. They're just being revealed in a way that challenges our intuition. Now, this might lead to an interesting thought. If appearances can be misleading in this way, then how confident can we be about what we're observing in general? And the answer is that we rely on careful measurement, on understanding the geometry of the situation, the timing of signals, and the physical processes involved. It's not enough to trust what something looks like. We have to understand how that appearance is constructed. And this brings us back once again to the role of light, because everything we see is mediated by it. Every observation is filtered through its travel time and its interactions. So when we talk about motion, especially at extreme scales, we're always dealing with a layer of interpretation, a reconstruction built from signals that have taken time to reach us. And sometimes, that reconstruction can create illusions that feel very real. If nothing can move through space faster than light, then how do we explain something that looks very much like it's doing exactly that? Not an illusion this time, not a trick of perspective or timing, something much larger, the universe itself. Because when astronomers began to look outward, far beyond our galaxy, they noticed something unusual. Galaxies were not just sitting in place, they were moving away from us, and not randomly. There was a pattern. The farther away a galaxy was, the faster it seemed to be receding. At first, this might sound familiar. Objects moving apart, speeds increasing with distance. That's something we can imagine. But as measurements became more precise, the numbers started to grow in a way that didn't quite fit with everyday intuition. For galaxies that are very far away, the rate at which they're receding from us can exceed the speed of light, which feels like a direct contradiction, because we've just spent all this time establishing that nothing can move faster than light. So what's happening here? To understand this, we need to make a small but important shift in perspective. Up to now, we've been thinking about objects moving through space, a car moving along a road, a spacecraft travelling between planets, a particle racing through a detector. In all of these cases, the motion happens within space, and the speed of light acts as a limit on that motion. But the expansion of the universe is not about objects moving through space in the usual sense. It's about space itself changing. And that difference matters, Imagine for a moment a simple analogy. Picture a balloon with small dots drawn on its surface. These dots represent galaxies. Now, as the balloon inflates, the surface stretches. The dots move away from each other, not because they're travelling across the surface, but because the surface itself is expanding. From the perspective of any one dot, all the others appear to be moving away, and the farther apart two dots are, the faster the distance between them increases, not because the dots themselves are moving quickly, but because there's more space between them to stretch. Now, this analogy isn't perfect, but it captures the key idea. The expansion of the universe is not like galaxies racing through space away from each other. It's space itself expanding, carrying galaxies along with it. And because of that, the usual speed limit doesn't apply in the same way. The speed of light limits how fast something can move through space, but it doesn't limit how quickly space itself can expand. So when we say that distant galaxies are receding faster than light, we're not saying they're moving through space at that speed. We're saying that the distance between us and those galaxies is increasing at that rate, because space itself is stretching. And that distinction is crucial, because it preserves the rule we've been building. Nothing locally moves faster than light. No object, no signal, no information. But on very large scales, the structure of space can evolve in ways that create effective speeds greater than light. Now, there's another layer to this, because if galaxies are moving away from us, and the farther ones are moving away faster, then there must be a point beyond which the recession speed exceeds the speed of light. And there is. This leads to something called the observable universe, the region of space from which light has had time to reach us since the beginning of the universe. Beyond that region, there are galaxies whose light will never reach us, not because they're hidden or obscured, but because the space between us and them is expanding too quickly. Even light moving at its maximum speed cannot close the gap. It's a bit like trying to swim toward a distant shore while the water itself is carrying you away faster than you can swim. No matter how strong you are, no matter how long you keep trying, you'll never reach it. So there are parts of the universe that are, in a very real sense, beyond our reach. Not just difficult to observe, but fundamentally unobservable. And this introduces a quiet boundary, not a physical wall, but a limit to what we can ever know. Now, it's worth pausing here, because this idea can feel a little unsettling at first. The notion that there are regions of the universe forever inaccessible, forever beyond observation. But there's also something gentle about it, because it reminds us that the universe is not just vast but dynamic. It's not a static backdrop where everything is fixed in place. It's evolving, expanding, changing over time, and we are part of that process. Now, there's another interesting consequence of this expansion, because if you look at very distant galaxies, the light we receive from them is stretched. As space expands, it stretches the wavelengths of light travelling through it. This is known as redshift. Light that was originally emitted at shorter wavelengths like blue or ultraviolet is stretched into longer wavelengths, moving toward the red end of the spectrum. And the greater the distance, the greater the redshift. This stretching is not because the galaxies are moving through space in the usual sense, but because the space between us and them is expanding. And this provides one of the key pieces of evidence for the expansion of the universe. Now, there's something quietly interesting about how all of this fits together. On small scales, within galaxies, within solar systems, even within clusters of galaxies, gravity holds things together. Space is not expanding in a way that pulls everything apart locally. But on larger scales, beyond those gravitational bonds, the expansion becomes dominant. Galaxies drift apart. Distances grow. And the universe continues to unfold. So when we ask whether anything can move faster than light, the answer depends on how we're asking the question. If we're talking about motion through space, the answer remains no. That limit holds. But if we're talking about the expansion of space itself, then things can appear to move apart at speeds greater than light. And this doesn't break the rules. It operates within them. It's simply a different kind of motion. Now, this distinction between moving through space and space itself expanding is one of those ideas that can take a moment to settle in, but once it does, it opens up a new way of thinking about the universe, because it shows that the speed limit we've been discussing is not a simple restriction on everything. It's a specific rule about how objects and information move within the structure of space-time. And that structure itself can evolve in ways that feel, at first glance, like exceptions, but are really just a deeper expression of the same underlying principles. Strangely enough, the rule we've been circling around this whole time comes with a quiet exception, but only if you look at it from the right angle. Up to now, the idea has been steady and consistent. Nothing can move through space faster than light. Not a particle, not a signal, not even information itself. It's a limit that seems to sit at the very foundation of how the universe behaves. And yet, just beneath that rule, there's something else happening. Something that doesn't quite break the rule, but definitely bends the way we think about it. Because while nothing can outrun light through space, space itself doesn't have to follow that same restriction. That might sound like a small distinction at first, almost like wordplay, but it turns out to be one of the most important shifts in perspective you can make. To ease into it, let's return briefly to something we touched on earlier, but look at it from a slightly different angle. When we talked about the expansion of the universe, we described galaxies moving away from each other, not because they're racing outward in the usual sense, but because the space between them is stretching. Now, instead of thinking about galaxies, try to focus only on the space itself. Imagine space not as an empty stage where things happen, but as something more active, something that can change, stretch, and evolve. In everyday life, space feels fixed. Distances don't suddenly grow while you're walking across a room. The ground doesn't stretch beneath your feet. The distance between two objects stays the same unless something physically moves. So it's natural to assume that space itself is stable. But on very large scales, the universe behaves differently. The distance between galaxies increases over time, even when those galaxies aren't moving through space in the usual sense, which means the space between them is expanding. And here's where things become interesting. If space can expand, then there's no strict limit on how quickly that expansion can happen, because the speed of light only limits motion within space. It doesn't limit the rate at which space itself can change. So in a very real sense, space can move faster than light. Or more precisely, it can expand in such a way that distances increase faster than light could travel between them. Now, this might feel like a loophole, a way of getting around the rule we've been building, but it's not quite that. Because even though space can expand at this rate, it doesn't allow for faster than light communication. No information is being transmitted faster than light. No signal is crossing space at an impossible speed. Instead, the structure of space itself is evolving, and that distinction keeps the rule intact. Now, there's a concept in physics that takes this idea even further, something known as the metric expansion of space. It sounds technical, but the underlying idea is quite gentle. It simply means that the way we measure distances changes over time. The metric, the system we use to define how far apart things are, is not fixed. It can stretch, and when it does, everything embedded within that space moves apart accordingly. Now, let's imagine a slightly different scenario. Instead of the entire universe expanding uniformly, picture a localized region of space where this stretching is much more intense. A bubble, if you like, where space expands rapidly in a specific direction. If you were inside that bubble, you might not feel anything unusual. Locally, everything would behave normally. But from the outside, it could appear as though that region is moving incredibly fast, even faster than light. This idea isn't just speculation. It's closely related to a concept known as the warp drive. Often discussed in science fiction, the warp drive doesn't involve an object moving through space at extreme speed. Instead, it involves contracting space in front of an object and expanding space behind it. So the object itself remains locally at rest, not exceeding the speed of light in its immediate surroundings, while the space around it carries it forward. In theory, this could allow for effective faster-than-light travel, not by breaking the rules, but by working around them. But there's a catch. Actually, several. The conditions required to create such a distortion in space are far beyond anything we currently understand how to achieve. They would likely require forms of energy or matter that we haven't observed, or at least haven't learned how to manipulate. So while the idea is fascinating, it remains, for now, firmly in the realm of theory. Still, it serves as a useful illustration, because it shows that the speed limit we've been discussing is not about preventing all forms of rapid change. It's about preserving the structure of cause and effect. As long as information doesn't travel faster than light within a local region of space-time, the rule holds. Now, there's another place where this idea becomes important: the early universe. Shortly after the Big Bang, the universe underwent a period of extremely rapid expansion, known as cosmic inflation. During this brief phase, space itself expanded at a rate far exceeding the speed of light. Distances between points grew incredibly quickly, faster than light could travel across them, and yet, this didn't violate the cosmic speed limit, because again, nothing was moving through space faster than light. Space itself was expanding. This period of inflation helps explain several features of the universe we observe today, including its large-scale uniformity. But it also reinforces the idea that space is not just a passive backdrop, it's dynamic. It can change in ways that feel, at first glance, like exceptions to the rules, but are actually consistent with them at a deeper level. Now, let's pause here for a moment, because there's something quietly profound about this. The fastest thing in the universe, light, sets a limit on motion within space. But space itself is not bound by that same limit. It can stretch, expand, and evolve in ways that create effects beyond that boundary, and yet through all of this, the structure of cause and effect remains intact. The universe maintains its coherence, its consistency. So the rule isn't being broken, it's being expressed in a more subtle way. And this brings us back to the question we've been following all along. What is the fastest thing in the universe? At first it seemed like a question about objects, then it became a question about limits, and now it's starting to look like a question about the structure of reality itself. Because speed, at this level, is not just about how quickly something moves, it's about how space, time, and information are connected, and how those connections define what is possible. Long after the idea of a universal speed limit had settled into place, another phenomenon began to quietly challenge the way people thought about distance and connection. Not by moving faster exactly, but by behaving as if distance didn't matter at all. It started with something very small. Two particles, not unusual on their own, but when prepared in a certain way, they could become linked, connected in a manner that didn't quite fit with the usual rules of separation. This connection is what we now call quantum entanglement, and at first glance it feels almost like a loophole. Because when two particles are entangled, measuring one seems to instantly affect the other, no matter how far apart they are. Not after a delay, not at the speed of light, instantly. Which raises a question that feels both simple and slightly unsettling. If something can happen instantly across any distance, doesn't that mean something has effectively travelled faster than light? To understand why the answer is more subtle than it appears, it helps to slow down and look carefully at what instant actually means in this context. Imagine for a moment that you have a pair of gloves. You place one glove in a box and send it to one side of the world. The other glove goes in another box and travels in the opposite direction. Once they arrive, someone opens one of the boxes and sees a left-hand glove. Immediately they know the other box must contain the right-hand glove. No signal was sent at that moment. No information travelled between the boxes when the first one was opened. The relationship was already determined. Now, entanglement is not exactly like this. In fact, it's stranger. Because before you measure the particles, they don't have definite states in the same way the gloves do. They exist in a kind of shared set of possibilities. Only when you measure one does a definite outcome appear, and at that same moment, the other particle's state becomes defined as well. This is where the sense of instantaneous connection comes from. But here's the important part. Even though the outcomes are linked, you can't control what result you get. When you measure your particle, you don't get to choose whether it ends up in one state or another. The result appears randomly, within certain probabilities. And because you can't control the outcome, you can't use this process to send information. That's the key. If you and someone far away each have one particle from an entangled pair, you can measure yours and immediately get a result. At the same time, their particle will reflect a correlated result. But neither of you can influence what that result will be. So there's no way to encode a message in it. No way to say, I'll make my particle do this to tell you something. The outcome is not under your control, and because of that, no usable information travels between the particles at the moment of measurement, which means that even though the connection feels instantaneous, it doesn't violate the cosmic speed limit. No signal is being sent faster than light. Now, this might feel like a technical distinction, but it's actually quite fundamental, because the speed of light doesn't just limit how fast things can move, it limits how fast information can be transmitted, and entanglement, for all its strangeness, doesn't allow for faster-than-light communication. It only creates correlations. Now, there's another layer to this that makes it even more intriguing. Because when these experiments were first proposed, even some of the scientists involved found the idea uncomfortable. Albert Einstein famously referred to it as spooky action at a distance. Not because it was magical, but because it seemed to imply a kind of connection that didn't respect the usual boundaries of space. For Einstein, who had helped establish the importance of those boundaries, this was deeply unsettling. He believed that there must be some hidden explanation, something beneath the surface that would restore a more intuitive sense of locality. But as experiments became more refined, the results consistently supported the predictions of quantum mechanics. Entanglement was real. The correlations were real. And they couldn't be explained by any local hidden mechanism, at least not in a way that matched the observations. So the universe, it seems, allows for connections that are not limited by distance in the way we might expect, but it still preserves the speed limit for information, which is an interesting balance, because it means that while two particles can be linked in a way that transcends space, that link cannot be used to send signals faster than light. It's as if the universe permits a kind of instant relationship, but not instant communication. Now, let's take a step back and think about what this means for our original question. What is the fastest thing in the universe? At first, entanglement might seem like a candidate. After all, if something happens instantly across any distance, it feels like it must be faster than anything else. But once we look more closely, we see that nothing is actually travelling. No particle is moving from one place to another at infinite speed. No information is being transmitted in that way. So while entanglement is deeply connected to the structure of reality, it doesn't represent a speed in the usual sense. It doesn't compete with light. It operates in a different category entirely. And this brings us to an important distinction. Speed applies to things that move or signals that travel. Entanglement is not about movement, it's about correlation, a relationship that exists without needing to be carried from one point to another. Now, there's something quietly fascinating about that, because it suggests that the universe has multiple ways of connecting things. Some connections are limited by speed, by the time it takes for light or other signals to travel. Others exist outside that framework, not as signals, but as shared states. And yet, even with these different kinds of connections, the overall structure remains consistent. The speed of light still defines the maximum rate at which information can move. Cause and effect remain ordered. The rule holds. So entanglement doesn't break the universe's rulebook. It reveals a different chapter of it, one where connection doesn't always require travel, but where the limits on communication remain firmly in place. And as we move forward, we'll continue to refine this idea, because not everything that feels fast is actually moving quickly, and not everything that moves quickly carries information in the same way. Speed starts to feel a little less straightforward once you separate two ideas that usually travel together: movement and information. At first, they seem almost identical. Something moves from one place to another, and in doing so, it carries information with it. A car arrives, and you know it has travelled. A sound reaches you, and you know something made it. Light enters your eyes, and you see an object. So it's easy to assume that whatever moves fastest must also be the fastest way to send information. But as we've been slowly uncovering, those two ideas don't always line up as neatly as they appear. And once you pull them apart even slightly, the question we've been following begins to sharpen in a new way. Not just what moves the fastest, but what can actually carry information the fastest, because that's the part that really matters. Let's start with something simple again. Imagine you're standing in a large dark field with a flashlight. You turn it on, and a beam of light travels outward. That light carries information. Anyone standing far away, when they see the beam, knows that you've turned it on. Now imagine instead that you're holding a long row of dominoes. You push the first one and the motion travels down the line. Each domino falls, triggering the next. The motion moves forward, but notice something interesting. No single domino travels the entire distance. Each one only moves a little. The movement that travels is actually a pattern, and that pattern carries information, the information that the first domino was pushed. Now here's where things become subtle. The speed of that pattern is limited by how quickly each domino can fall and trigger the next. You can't make it propagate faster than the physical process allows, and that's true for all systems that transmit information. There's always a mechanism, a chain of interactions, a process that takes time. Now, let's connect this to something we discussed earlier, the laser pointer sweeping across a distant surface. The spot of light can appear to move faster than light if the surface is far enough away and the angle changes quickly. But that spot is not carrying information from one point on the surface to another. Each point is being illuminated by a different part of the beam. There's no single entity travelling across the surface, so even though the motion appears fast, it doesn't represent a transmission of information at that speed. And that's the key distinction. Movement can appear fast, patterns can appear to move fast, but information, something that can be used to send a message, to influence a distant point in a controlled way, is constrained. It cannot exceed the speed of light. Now, let's bring this back to quantum entanglement for a moment. When two particles are entangled, measuring one instantly determines the state of the other. At first glance, it feels like information has travelled instantly. But as we saw, there's no control over the outcome. You can't choose what result to send. So while there is a connection, there's no usable transmission of information, no message, no signal, and without that, there's no violation of the speed limit. Because the limit applies to information, not just correlation. Now here's where things become even more interesting. Because even within the concept of light, the fastest thing we've been discussing, there are different ways to think about how information travels. Light is a wave, an electromagnetic wave, and waves have different characteristics. There's the phase velocity, which describes how the peaks and troughs move. There's the group velocity, which describes how the overall shape of the wave packet moves. And then there's the signal velocity, which is the speed at which information is actually transmitted. In most everyday situations, these are all effectively the same. But under certain conditions, especially in complex materials, they can differ. There are situations where the phase velocity of a wave can exceed the speed of light. But again, this does not carry information. The signal velocity, the speed at which a new piece of information can be transmitted, remains at or below the speed of light. So even within light itself, the universe maintains this distinction. Not everything that moves quickly is carrying information, and not everything that looks like it's moving quickly is doing so in a way that matters for communication. Now, let's consider a more intuitive example. Imagine you're watching a long line of people standing side by side. If one person raises their hand, and then the next person does the same and so on, the motion can travel down the line. You could, in principle, make that wave move very quickly if everyone reacts fast enough, but the speed of that wave is limited by how quickly each person can respond. Now imagine instead that each person independently decides to raise their hand at a specific time, based on a clock they all share. From a distance, it might look like a wave moving down the line, even if no one is reacting to their neighbour. In that case, the motion of the wave is not carrying information from one end to the other. It's just a pattern created by coordinated timing, and that pattern could, in theory, appear to move very fast, even faster than light. But again, no information is being transmitted along the line. Each person is acting independently. This is similar to many of the faster-than-light illusions we've discussed. They involve patterns, sequences, or projections, not actual signals travelling from one place to another. Now, why does this distinction matter so much? Because the structure of the universe depends on it. If information could travel faster than light, then cause and effect could become scrambled. Messages could arrive before they were sent. Events could influence their own causes, and the consistent ordering of the events would break down. But as long as information is limited to the speed of light, that structure remains intact, no matter how strange or complex the behaviour of motion appears. So when we ask what actually travels the fastest, we have to be precise. Is it an object, a pattern, a correlation, or information? Because only one of those is truly constrained in a fundamental way: information. And the fastest speed at which information can travel, as far as we know, is the speed of light in a vacuum. Everything else, every apparent exception, every surprising phenomenon, fits within that boundary once we look closely enough. Now, this leads to a slightly different perspective on our original question. Instead of asking what moves the fastest, we might ask what sets the limit for how quickly anything can influence anything else. And the answer once again points to light, not just as a fast-moving entity, but as a fundamental constant, a boundary that defines how the universe connects events across space and time. For a moment, it's tempting to take everything we've explored and turn it inward, not toward particles, not toward distant galaxies, but toward something much more personal. Could we ever go that fast? Not in theory, not in equations, but in a way that involves us, our bodies, our technology, our journeys across space. Could we ever approach the speed of light, not just as an idea, but as an experience? At first, the answer feels like it should be yes. After all, we've already seen that humans can accelerate particles to incredible speeds. We've built machines that push tiny bits of matter to within a fraction of the speed of light. We've launched spacecraft that travel faster than anything else we've ever made, so it seems like a matter of scaling up. More power, better materials, larger systems, just a matter of time. But this is where things begin to slow down again, not in motion, but in possibility. Because the closer you look, the more you realise that reaching those extreme speeds is not just a question of engineering, it's a question of energy. And the amount of energy required grows in a way that quickly becomes overwhelming. Let's return to the idea we touched on earlier. As something with mass accelerates, it requires energy to increase its speed. That part feels familiar. But as it gets closer to the speed of light, each additional increase in speed demands more energy than the last. Not just a little more, a lot more, and then even more than that. The relationship isn't linear. It's not even comfortably exponential in the way we might expect. It climbs steeply, sharply, approaching a point where the required energy becomes effectively infinite. So while a particle can get extremely close to the speed of light, pushing something larger, something with significant mass, becomes extraordinarily difficult. Now imagine trying to accelerate something the size of a spacecraft. Not just the structure itself, but everything inside it. Life support systems, shielding, fuel, and perhaps eventually people. The energy required would be enormous, far beyond anything we currently produce. Even if we imagine future technologies, more efficient engines, better energy storage, the gap remains vast. And it's not just about reaching high speed, it's about maintaining control. At such speeds, even a tiny particle of dust becomes a significant hazard. Collisions at near-light speeds would release tremendous energy, enough to damage or destroy a spacecraft. So any journey at those speeds would require not only immense energy, but also extraordinary protection. Now there are ideas that try to work around these challenges. Concepts that don't rely on accelerating a massive spacecraft directly, but instead use lighter systems, for example, light sails. These are large, reflective surfaces that can be pushed by light itself, either from the sun or from powerful lasers. Because they don't carry fuel in the traditional sense, they can, in principle, be accelerated continuously over long periods. Given enough time and a strong enough source of light, they could reach a significant fraction of the speed of light. But even here, there are limits. The acceleration is gradual, the distances involved are enormous, and the challenges of steering, communication, and survival remain. Now let's consider another angle. Even if we could reach such speeds, what would the journey feel like? This is where the earlier ideas about time dilation return, but now with a more personal perspective. From the point of view of someone travelling at near light speed, time would pass more slowly relative to those who remain behind. So a journey that might take decades or centuries from an outside perspective could feel much shorter to the traveller. In a sense, the universe ahead would contract. Distances would shrink. The journey would become more manageable, at least from the traveller's own experience. This leads to a curious possibility. Even if reaching the speed of light is impossible, getting close to it could allow for journeys across vast distances within a human lifetime, from the traveller's perspective. But there's a trade-off. When the traveller returns, or communicates with those who stayed behind, they would find that much more time has passed. Years, decades, perhaps even longer. So the journey would not just be through space, but through time. Now this idea has been explored in many ways, both in science and in storytelling. But it's grounded in real physics. Time dilation is not just a theoretical concept. It's been observed, measured, confirmed. So while near light speed travel might remain out of reach for now, its consequences are well understood. Now there's another question that often follows. If accelerating to near light speed is so difficult, could we find a way to bypass the need for acceleration altogether? This is where ideas like warp drives and wormholes come into play. Instead of moving through space at extreme speeds, these concepts involve altering space itself. Contracting space in front of a spacecraft, expanding it behind, or creating shortcuts that connect to distant points directly. In theory, this could allow for faster-than-light travel without violating the local speed limit. But in practice, these ideas come with their own challenges. They often require forms of matter or energy that we don't currently know how to create or control. They may involve conditions that are unstable or difficult to sustain, so for now they remain possibilities rather than realities. Still, they serve as a reminder that the question of speed is not just about motion. It's about how we navigate the structure of space-time itself. Now, bringing this back to something more grounded, it's worth noticing how far we've already come, from walking speed to orbital velocity, from early aircraft to spacecraft leaving the solar system, from simple machines to particle accelerators probing the limits of physics. Each step has expanded our understanding of what's possible, and while the speed of light remains out of reach, the journey toward it has revealed something more important. It has shown us the rules, the boundaries, the structure that defines motion at the deepest level. So when we ask whether we could ever travel that fast, the answer is layered. In a strict sense, no. Nothing with mass can reach the speed of light. But in a broader sense, we can approach it. We can explore the effects that emerge near that boundary. We can design systems that operate within those limits. And in doing so, we learn not just about speed, but about the nature of reality itself. Consider for just a moment how steady time usually feels. It moves forward at a constant pace, second by second, minute by minute, without hesitation and without variation. Your clock ticks evenly. Your thoughts unfold in a continuous stream. Everything around you seems to share the same rhythm, as if time itself were a universal current carrying everything along together. That's the assumption most of us live with. Time is constant. Time is shared. Time flows the same for everyone. But as motion approaches the extreme, as speed begins to press against that cosmic boundary we've been circling, this quiet assumption starts to loosen. Not dramatically at first, not in a way that would interrupt your day or make you suddenly aware that something has changed. But gradually, predictably, time begins to behave differently. And what's most surprising is not that it changes, it's how it changes. Because it doesn't feel different from the inside. Let's return, gently, to that spacecraft. You're still inside it, still accelerating, still moving faster and faster through space. The journey has been smooth, controlled, almost uneventful from your perspective. Your body has adapted. Your surroundings feel stable. Now imagine that your speed has reached a point where it is extremely close to the speed of light. Not equal, never quite equal, but close enough that the effects we've been describing are no longer subtle. From your point of view, nothing unusual has happened to time. Your watch ticks normally. Your breathing follows its usual rhythm. If you speak, your voice sounds the same. If you think, your thoughts unfold at their usual pace. Everything feels unchanged. But far away, from the perspective of someone observing your journey, something remarkable is happening. Your time is slowing down. Not metaphorically, not as a figure of speech, but in a real, measurable sense. If they could see your clock, they would notice it ticking more slowly than their own. If they could observe your movements, they would appear slightly delayed, stretched out compared to their frame of reference. And the faster you go, the more pronounced this difference becomes. Now, let's pause with that idea, because it introduces something that feels almost impossible at first. Time is not absolute. It doesn't flow at the same rate for everyone. Instead, it depends on motion. This effect is known as time dilation, and while the name might sound technical, the concept itself is quite direct. Moving clocks run slower, that's it. But the implications of that simple statement are far-reaching. To make this feel a bit more grounded, imagine two identical clocks. One stays on Earth, the other is placed on a spacecraft that travels at very high speed for a long period of time before returning. When the spacecraft comes back, the two clocks are no longer synchronized. The one that travelled will show less elapsed time. From its perspective, the journey felt normal, but compared to the clock that remained on Earth, it has experienced less time. And this is not just a thought experiment, it has been tested. Clocks placed on fast-moving aircraft or satellites orbiting Earth show measurable differences compared to those on the ground. The effect is small at those speeds, but it's real, and as speed increases, the effect grows. Now, let's bring this back to our near-light speed journey. If you were travelling at such speeds for what feels like a few years to you, much more time could pass for those who remain behind. Decades, centuries, depending on how close you are to the speed of light. So in a sense, high-speed travel becomes a kind of one-way journey into the future. Not because you're skipping time, but because you're experiencing less of it relative to others. Now there's another side to this that's just as interesting. From your perspective inside the spacecraft, it's not just your own time that feels normal, it's everything around you. Your environment, your processes, your internal sense of duration, all of it remains consistent. What changes is the relationship between your time and the time of the outside universe. And this leads to a kind of symmetry. From your point of view, it might seem as though time in the outside universe is moving faster. Events there appear compressed, accelerated, while from their point of view, your time appears slowed. Two perspectives, each valid, each consistent within its own frame of reference. Now, there's something quietly important about this, because it means there is no single universal timeline that everyone shares. Instead, each observer carries their own measure of time shaped by their motion, and yet, despite this flexibility, the universe remains consistent. Events that are causally connected, those that can influence each other, still maintain their order. The structure holds. Now let's take this idea a little further. As your speed increases, time dilation becomes more extreme. Closer and closer to the speed of light, your time slows more and more relative to others. In the limit, as you approach that boundary, the effect grows without bound. From the outside perspective, your clock would appear to slow almost to a stop. Almost, but never completely. Because reaching the speed of light would require infinite energy, and so this extreme state remains just out of reach. Still, even approaching it leads to profound consequences. It means that the faster you move, the less time you experience compared to someone at rest. So speed and time become deeply connected. Motion doesn't just change where you are, it changes when you are, relative to others. Now, there's something else to notice here. Because time dilation is not just about speed, it's about the structure of space-time itself. Earlier, we talked about how space and time are not separate but interconnected. Changes in one can affect the other. At high speeds, this connection becomes more apparent. As time slows down, distances contract. As distances contract, the journey ahead becomes shorter from your perspective. Everything adjusts in a coordinated way. Not randomly, not independently, but as part of a single system. And at the center of that system sits the speed of light, the constant that everything else adjusts around. Now, returning to our original question, what is the fastest thing in the universe? We can see that the answer is not just about motion, it's about how motion affects time. Because as you approach the maximum speed, time itself begins to change. And that change is not a side effect. It's a fundamental part of how the universe enforces its limits. So time dilation is not just an interesting consequence, it's part of the rule. A way of ensuring that the speed of light remains the ultimate boundary. After everything we've followed so far, there's a quiet shift that starts to happen in the question itself. At the beginning, it felt simple, almost like a quiz. What is the fastest thing in the universe? The kind of question that suggests a clear answer, something you can point to, name, and feel satisfied with. Light. That seemed to settle it. But now, after moving through motion, perception, relativity, expansion, and even quantum behavior, the question doesn't feel quite as straightforward anymore. Because the more closely you look, the more it begins to change shape. Not dramatically, not all at once, but enough that the answer starts to feel less like a single object and more like something deeper. So instead of rushing toward a conclusion, it helps to pause and look at what we've actually uncovered. We've seen that everyday speed is relative. A car is fast compared to a person, a plane is fast compared to a car, but all of these exist within a narrow range. We've seen that sound once felt like a natural limit, only to be replaced by something far greater. We've seen that light travels at a constant speed, not because it's being pushed to a limit, but because that limit is built into the structure of space and time. We've seen that as objects approach that speed, time slows down, distances contract, and energy requirements grow without bound. We've seen that nothing with mass can reach or exceed that speed, and that faster than light motion would disrupt the order of cause and effect. We've seen that space itself can expand in ways that create the appearance of faster than light separation without breaking the underlying rules. We've seen that quantum entanglement allows for instantaneous correlations, but not the transmission of information. And we've seen that not everything that appears fast is actually carrying anything from one place to another. So when we return to the question, what is the fastest thing in the universe? Something subtle has changed. Because fastest now depends on what you mean. If you mean the fastest object, then light, or more precisely massless particles like photons, moves at that fundamental speed. If you mean the fastest transmission of information, then again light defines that limit. But if you mean the fastest appearance of motion, then there are patterns, projections, and expansions that can seem to exceed it. And if you mean the fastest connection, then entanglement introduces something that doesn't fit neatly into the idea of speed at all. So the answer begins to branch. And once it branches, it becomes less about choosing one option and more about understanding the framework that connects them. Because perhaps the fastest thing is not a thing in the usual sense. Perhaps it's a limit, a boundary, a relationship. Think about it this way. In everyday life, speed is something objects have. A car has a speed, a runner has a speed, a plane has a speed. But at the scale of the universe, speed becomes something that defines how objects can interact. It's no longer just a property, it's a rule. The speed of light is not just how fast light moves, it's how fast anything can move through space. It's how quickly one event can influence another. It's how fast information can propagate. So instead of being one competitor in a race, it becomes the track itself, the boundary that everything else moves within. Now, there's something quietly elegant about that, because it means the answer to the question is both simple and layered at the same time. Simple in the sense that light represents the maximum speed for motion and information. Layered in the sense that what we really care about is not just the motion of objects, but the structure of connections. And this leads to a slightly different way of thinking about fast. Instead of asking what moves the fastest, we might ask what defines the fastest possible change. What sets the limit for how quickly the universe can evolve from one state to another? And that brings us back once again to that same constant, the speed of light in a vacuum. Now there's another perspective that emerges from all of this, because if speed is tied so closely to space and time, then changing your speed changes your experience of both. At extreme velocities, time slows down, distances contract, and the relationship between events shifts. So, fast is not just about covering distance quickly. It's about how your path through space-time unfolds, and in that sense, the fastest journey is not necessarily the one that looks fastest from the outside, it's the one that changes your experience of time the most, which is a slightly different way of thinking about it. Now, bringing this back to something more intuitive, it's worth noticing how far we've come from the original simplicity of the question. What started as a search for the fastest thing has become an exploration of motion, perception, and the structure of reality. And along the way, the answer has become less about naming something and more about understanding a principle. So when someone asks what the fastest thing in the universe is, you could still say light, and you wouldn't be wrong. But now that answer carries more meaning. It's not just a fact, it's a doorway into everything we've been exploring. A reminder that speed, at its deepest level, is not just about how quickly something moves, but about how the universe itself is organized. Instead of trying to push the idea of speed any further, it helps to pause and ask something slightly different. Not what is the fastest thing, but whether that question, as simple as it sounds, is actually pointing us in the right direction at all. Because after everything we've explored, the answer no longer feels like it belongs to a single object or a single measurement. It doesn't feel like something you can hold in place and label cleanly. It keeps expanding, shifting, connecting to deeper layers of how the universe works, and that's usually a sign that the question itself might be too narrow. Not wrong, just incomplete. So let's take a step back gently and look at what we've really been uncovering this whole time. At the beginning, speed felt like a property, something objects have. A car has a speed, a plane has a speed, a particle has a speed. Faster means more distance in less time. Simple, intuitive, easy to compare. But as soon as we moved beyond everyday experience, that simplicity started to fade. Speed became relative, dependent on perspective. Two observers moving differently could disagree about how fast something was going, and both would be correct within their own frame of reference. That alone already makes the idea of a single fastest object a little less solid. But then we found something that seemed to resist that relativity. Light. No matter how you move, no matter how you measure it, the speed of light remains the same. And at first, that feels like the answer we were looking for. But then that answer started to open up. Because the speed of light isn't just about light, it's about space and time. It defines how distances and durations adjust relative to motion. It sets the limit for how quickly information can travel. It preserves the order of cause and effect. So instead of being just one example of something fast, it becomes something more like a rule, a constraint, a structural feature of reality. Now, if speed is tied so closely to space and time, then asking about the fastest thing is really asking about how space and time behave. And that's a different kind of question. Because space and time are not things that move. They are the framework within which motion happens. So what we've been circling around is not just speed, but the geometry of space-time itself, how it stretches, how it contracts, how it connects events, and how that connection is limited. Now let's think about this from another angle. When you ask what the fastest thing is, you're implicitly imagining something travelling from one place to another, a start point and an end point, a journey. But in many of the most important cases we've discussed, that picture doesn't quite apply. Quantum entanglement doesn't involve something travelling, it involves a relationship. The expansion of the universe doesn't involve galaxies moving through space in the usual sense. It involves space itself changing. Even the apparent faster-than-light motions we talked about are not objects crossing space, but patterns created by timing and perspective. So again, the idea of speed as simple motion begins to feel a bit limited. It doesn't capture everything that's happening. Now there's another layer to this, because speed, in the way we usually think about it, depends on distance and time, distance divided by time. But both distance and time, as we've seen, are not fixed. They change depending on motion. They are not absolute. So if the quantities that define speed are themselves flexible, then speed is not a fixed property in the way we might expect. It's something that emerges from the relationship between space and time, and that relationship can vary. So perhaps asking for the fastest thing is a bit like asking for the longest shadow without specifying the light source. The answer depends on the context. Now none of this means the question is meaningless, far from it. It's actually a very useful question, because it leads us to discover these deeper principles. But once we've discovered them, the question evolves. Instead of asking what is the fastest thing, we might ask, what is the maximum rate at which anything can influence anything else? And that brings us back to the idea of information. Because in physics, what really matters is not just motion, but interaction. One event affecting another, one part of the universe influencing another part, and that influence has a limit, the speed of light. Now, there's something quietly satisfying about that, because it reframes the question in a way that connects all the pieces we've explored. Light is not just fast, it defines the fastest possible connection, the fastest possible cause, the fastest possible change that can propagate through the universe. And that's a more complete answer, but even that might not be the end of it. Because there's another perspective, one that steps even further back. Instead of focusing on speed at all, we could ask about the structure of reality. What determines how things are connected? What sets the rules for how events unfold? And from that point of view, speed becomes just one aspect of a larger system. A system that includes space, time, energy, and the relationships between them. So the question shifts again, from what is fastest to what defines the limits of change. And the answer to that is not a single object, it's the structure of space-time. Now, let's bring this back to something more intuitive, something you can feel. When you experience motion, what you're really experiencing is change over time. Something is different from one moment to the next, and the faster that change happens, the faster something feels. But at the deepest level, the universe is not just a collection of moving objects, it's a network of events, each connected to others by relationships. and the speed of light defines how quickly those relationships can form. So instead of thinking about the fastest thing, it might be more accurate to think about the fastest connection, the fastest way for the universe to update itself, the fastest way for one part of reality to affect another, and that, once again, leads us back to the same place. Not because we're going in circles, but because we're approaching the idea from different angles. Light, or more precisely, the constant speed associated with it, is not just a speed, it's a limit on how quickly anything can happen in a connected way. Now, there's something quietly calming about that, because it means the universe has a kind of built-in pacing. Things don't happen instantly across arbitrary distances. There's always a finite time for connections to form, a rhythm to how events unfold, and that rhythm is set by a fundamental constant. So perhaps the question was never just about finding the fastest thing, it was about discovering that rhythm, understanding the pace at which the universe operates, and once you see it that way, the answer becomes less about competition and more about structure. Not what wins the race, but what defines the track. Somewhere along the way, without really noticing the exact moment it happened, the question changed. It began as something simple, almost playful, a curiosity you could hold lightly. What is the fastest thing in the universe? The kind of question that invites a quick answer, something neat and satisfying. And now, after moving through all of this, motion, light, time, space, information, it no longer feels like that kind of question. It feels quieter. Less about finding an answer and more about understanding a boundary. Because the universe, in its own steady way, doesn't seem to care about fast in the way we do. It doesn't race. It doesn't compete. It simply moves. Or more precisely, it allows movement within a structure that is already defined. And within that structure, there is a limit. Not as a restriction, not as something holding things back, but as something that gives everything else meaning. The speed of light. Not just as something that travels quickly, but as something that defines how quickly anything can happen, how quickly one event can reach another, how quickly change can spread. And once you begin to see it that way, the idea of speed softens a little. It stops feeling like a contest, stops feeling like something to push against, and instead becomes part of the quiet rhythm of the universe itself. Now, if you take a moment to think about where you are, not just physically, but in terms of motion, something interesting begins to settle in. You might feel still, sitting, lying down, resting. But the Earth beneath you is turning. The planet is orbiting the Sun. The Sun is moving through the galaxy. And the galaxy itself is part of a much larger motion. All of it happening at speeds that, in another context, would feel extraordinary. And yet you don't feel any of it, because motion, at its most constant, disappears into the background. It becomes part of the environment, something you don't need to think about, something you can simply exist within. And there's something gently reassuring about that, because it means that even in a universe defined by motion, by change, by expansion, your experience of it can remain calm, steady, grounded. Now think again about light. Every time you open your eyes, you're receiving information that has travelled across space. From nearby objects, the delay is so small it feels immediate. From the sun, it's a few minutes. From distant stars, years. From distant galaxies, sometimes millions or billions of years. So when you look out into the night sky, you're not just seeing space. You're seeing time, layers of it, moments from different parts of the universe arriving together, gently overlapping in your field of view. And all of it is limited, shaped, paced by that same constant speed. Nothing arrives instantly. Everything takes time. And that time gives structure to what you see. Now there's something else to notice here. Because while we've been focusing on speed as a limit, it's also what makes connection possible. If information could travel instantly, there would be no sense of distance, no separation. Everything would be immediate, overlapping, indistinguishable. But because there is a limit, because signals take time, the universe has structure. Things are here or there, now or later, cause and then effect. And within that structure, experiences can unfold, stories can happen. You can sit where you are, listening, thinking, reflecting, while light from distant places continues its quiet journey toward you. Now, returning to the idea of travel, of moving quickly, of reaching faraway places, there's a subtle realization that comes with everything we've explored. Even if we could move incredibly fast, even if we could approach that cosmic limit, we would still be moving within this structure. We would still be part of the same system. Time would shift, distances would change, but the underlying rules would remain. So the dream of moving faster and faster, of reaching the edge of what's possible, doesn't take us outside the universe's rhythm. It brings us closer to understanding it. Now, there's something quietly poetic, but also very grounded, about the idea that the fastest thing is not something you can outrun, not something you can chase and catch, but something that defines the very act of chasing, the very possibility of motion. And once you see it that way, the question we started with begins to settle into a kind of stillness, not because it no longer matters, but because it has unfolded into something larger than itself. So instead of asking what is the fastest thing, you might find yourself noticing something else. That everything around you is already moving, already part of a system that has limits, but also consistency. A system where change happens at a finite pace, where connections take time, where events unfold in an order that can be followed. And within that, you don't need to move at extraordinary speeds to be part of something vast. You already are. Now, as this comes to a close, there's no need for a sharp ending, no final conclusion that ties everything up neatly. Because the universe doesn't really work that way. It continues, quietly, steadily. Light continues to travel, space continues to expand, time continues to pass, differently for different observers, but always moving forward within its own frame, and you remain here, in your own frame, experiencing it at your own pace. So perhaps the most calming part of all of this is not how fast things can go, but the fact that they don't need to go any faster. The limit is already there, built in, holding everything together, and you can simply rest within it, letting the motion of the universe carry on whether you think about it or not. Because even in a universe defined by speed, there is always room for stillness, and that stillness, in its own quiet way, is just as much a part of the story as anything that moves.